All right. Good evening, everyone. Again, welcome back. Today, I'm going to cover a few topics, basically. First one is grouting, and then the soil anchor, then soil nailing, and then soil, organic soil stabilizations, mostly the peat soil, and then also MSC wall design. So many different topics today. So first thing is, first I'm going to talk about the grouting. So grouting, so here, basically this is another chemical, you can say the chemical admixture class we discussed about the chemical admixture. So this is a similar type, it's a chemical you are injecting into the ground to the soil to improve the strength of the soil. So for this lecture, so basically I'll talk about grouting. There are different types of grouting. What are the different material used for the grouting? What are the different suspension grouts, solution grouts? We'll talk about that. And then how to design the grouting technique, basically. And then what are the different parameters you need to consider? So first thing is grouting is a process, as I mentioned, like a fluid-like material, either suspension or solution or emulsion form, are injected to the subsurface, to the ground, to improve their geotechnical properties. It can be for the soil, it can be for the rock also. So the main purpose of the grouting are to decrease the permeability. So permeability need to decrease the water, control the water, basically. So most of the time in the dam, you can just use a grout curtain. Okay, densification to increase the compressibility of the settlement, to mitigate liquefaction, to increase the shear strength, reduce expansion of clay soil, and then filling large voids. So most of the cases, we just if there is a large void, we just fill it with the grout material, where they're compensating for the lost ground. Sometimes we have to be careful. Sometimes if you apply too much pressure, the foundation, it will create, again, damage to the structures. So objective of grouting, the expansion of clay soil, addition of support of the existing structure. So basically underpinning or any other structures, basically, we can do. So advantage here in compared to other methods, so no need of removal or replacement. So whatever the soil is there, so just inject some grout and then that will be done. So effective for underpinning, as I mentioned, protecting existing structures, easy to access and operate within constrained space, and then low mobilization cost. So these are the advantage. Limitation of this grouting is the quantity of grout is hard to estimate. We don't know what type of, how much is the hole inside the ground. So that is difficult to estimate. Effectiveness of some application cannot be predicted. So then when the grouting is done, so it is difficult to check. Area of improvement is sometimes uncertain. Grouting may cause ground movement and distress of the existing structure. Suppose you put too much pressure, the grout material can cause a heave and other problems. So, and then also if you're using some chemicals into the ground, so that also contains toxicity and adverse effect to the groundwater or underground environment. And for that, obviously, we need a specialty contractor. So here, as I mentioned, like it is when the foundation constructed below the groundwater table, and in that case, if you use the grout, that will be, it can solidifies, and then it will forming an impermeable barrier. Okay, so again, so you see the deeper the foundation, the longer time needed to be constructed, and therefore more benefit gained for the grouting as compared to the dewatering. So when there is a situation, so you can use that grouting. When there is a difficulty in access and foundation levels, in that cases, generally for the CT area or the tunnel shaft, sewer, or subway construction, there, if you want to control the water, so it is easy to use grout. Okay, and also when the different geometric dimensions, foundation are complicated, so in that case, the grouting is suitable. So what you need to do basically, you take the grout material, mostly cement and water, or maybe different polymers, sometimes the cement and fly ash. So what you mixed it, and then in a mixer, and then agitate it, and then pump through a the nozzle and pumped to the particular site. So here you see here that the diameter of the of the pump is around 30 to 50 millimeter diameter. Again, it depends on what type of grouting method you're using. So this is the typical grouting component and setup. You see over here the grout mixer, grout mixer. So basically the grout material and add water or some polymer and then agitate it, and then grouting pump, you can just inject it to the grout hole. So grout hole. So the thing is, while injecting the grout hole, so while below the ground, you need to apply more pressures, and then when you just the grouting pipe, you need to just lift it up. The pressure should be less. So depending on how much is the overburden pressure. So we will discuss about that also. So basically more pressure and then slowly, lift it up and then less pressure. So depending on the function, the grouts are the following types, different types of grout. So one is the permeation grout or penetration grout. Then compaction or controlled displacement grout, hydrofracturing or uncontrolled displacement grout, jet or replacement grout or displacement grout, and then last one is the compensation grout. So there are different types of grout, and how you what are the different advantages and disadvantages, what are the different pressure you need to apply for different types of grout, and what type of material or the particle size is suitable. So we need to check, and from there you can find out whether that material or any material is suitable for this type of grouting. So we need to later on, you'll see that we need to find out the groutability ratio. And from there, we can find out that what type of grout, the different types of grouting method is suitable for a particular type of grout. So this is first one is the permeation grouting. So basically just grout hole to the make a hole and then inject the grout. And basically, you're not applying too much pressure. So just flow into the in the soil. So mostly it should be granular type soil, and it should be very loose type of material. The second one is the compaction grouting. So we apply a little bit of pressure so that the grout material is pushed, the soil and compact the nearby soil. Okay. Then the hydrofracturing. So most of the time, so we apply too much pressure, and then so just for example, you are injecting through a fractured rock. So we apply pressure and then grout material go and fill that hole of the rock. Okay. So but if you apply too much pressure, that is not good also. It will create more damage and then good. So and then the jet grouting, also you can do like a deep mixing column. So using jet grouting, so there are air and water, and there are 2-3 valves, and then you just inject the grout and then rotate it and mix it, and forming a column of the grout material. And last one is the compensation grout. Okay. So first one, as I mentioned, the permeation grout or penetration grout. This is the most common and oldest grout method. So typically used for sandy type soil, and the soil with permeability less than 1 times 10 to the minus 6 meter per second. Less than that is not this type of if the permeability is very low for clay type of soil, this grout is not suitable. This is suitable for only for sandy type soil. Just inject the grout and then it will flow at its own. Not too much pressure. Then this is the permeation grouting. Different types of grouts. We'll talk more about that. What are the different types of grout material generally used? And then also when you pump this, so you need to know the grout material's viscosity of the material. So it is not water, right? It is mixed with water and some grout material. And when the flow takes place, obviously you need to know that viscosity of the material, and then also what type of flow, Newtonian flow or non-Newtonian flow. There are all these different things. We'll talk about that. So again, for permeation grouting, the cement, if it's a cement, so there are different water to cement ratios, like 2:1 to 10:1, depending on the site or what type of strength you need. Gravel, so this is suitable for gravel to coarse sand, and the permeability should be more than 5 times 10 to the minus 4 meter per second. Remarks is you see here the clay added to reduce the cement content sometimes. Bentonite, if you are using bentonite slurry, bentonite and water, so is 4:1 to 10:1. This is also gravel to fine sand. Sometimes the cement added to increase the permeability, increase the permanence. So basically, for long-term durability. Chemicals, sometimes you use different type of solution, silicate or acrylic resins and others. So also, permeability should be more than 1 times 10 to the power minus 6 meter per second. And the grout hole spacing should be 2 to 5 meters. So this is for the permeation grouting. Then the next one is the compaction grouting or controlled displacement grouting. So what you do, basically injection of a very stiff pumpable grout mixture, very high pressure into the specified area of the soil. So basically you see over here, the grout material will displace the soil nearby. So in this situation, you see the grout remains more or less intact as a mass and exert pressure on the soil or rock and compact thereby dense. So compacting nearby soil and weaker zone. So basically you can densify the nearby soil. Then the compaction grouting is most commonly done in stages, working from the bottom or deep injection, then up, since this is the fastest method. So basically you inject the bottom and then the pressure is more and then just lift up, okay, and then inject the grout material. So however, top-down injection is often used for shallow injection. So depending on the situation, so we can use different types. So compaction grout techniques are pre-constructed site improvement to arrest foundation settlement. So rectify sinkhole problems if there is any, or to lift or any level of slab or foundation. So inject the grout, it can rectify, so that compact the soil, or it can, rectify the foundation or any, settling structures. So displacement grout, again, what are the different types of material? It can use like a cement, bentonite, water, soil, all these different types of material. And then also grout hole spacing should be 1.5 to 5 meter. And the grout pressure is up to, 4,000 kilonewton per meter square. So you have to inject pressure so that the adjoining soil will be compacted. Okay. So this is suitable for all type of soil, loose grained soil, soft grained soil also are not, which are not saturated and filled underground for filling underground cavities. Okay, not saturated. Okay, we can do that. So displacement compaction grout following situations. What situation you can use? The densification of the thin strata of underlying dense soil are located in considerable depth. So you can use that. So densification of the pocket of loose soil beneath the foundation or floor slab, so that inject the grout and that soil layer will be filled with grout material and increase the strength. Filling of large underground cavities caused by the broken underground utility lines or piping or erosion and dissolution. So in that situation, there are different situations you can use this compaction. So over here, just for example, thin strata, as I mentioned, the loose soil beneath the dense soil. So in that situation, it is good. There is a loose soil, so you can inject the grout material in the loose soil, then it will be good. So densification of the loose soil, so you can, the grout hole, and then inject pressure. So the adjoining soil over here, this will be densified, okay, and then go up. So here, slab jack, sometimes the floor slab is settling because the erosion and other things. So what you can do is just grouting zone over here so that it can uplift. So this is a sinkhole. Again, it is commonly used for the sinkhole, but again, it is very difficult to estimate how much quantity of material is needed for the sinkhole. Okay. Then third one is the hydrofracturing on uncontrolled displacement grout. Okay. So here in this case, the grouting pressure is greater than the tensile strength of the rock or being grouted. So if there is a crack, you just inject more with higher pressure, so that will fill that gap. Okay. The latter material fails and the grout rapidly penetrates in the fracture zone. Thus, the lenses of nearby solid grout and projected with the densified region into the in-situ soil or dense packed and displaced rock masses. So here you see here the grout pressure as high as 4,000 kilonewton per meter square. Diameter of this hole is 100 millimeter. So basically, again, used lean slurry cement, soil, and water injected to the soil with high pressure to fracture the soil, and then fill that with the grout material. Then jet grouting. So jet grouting is introduced in Japan in 1970s. So basically, here this method excavates a cavity by action of the horizontal high pressure air and water jet, and then the grout will also injected over there. And then basically the water to cement ratio over here 0.5 to 1 or 2:1 depending on the need. And then the grout hole spacing is 0.5 to 2 meter, and grout pressure is really very high over here. You see 30,000 to 60,000 kilonewton per meter square. So and this can be applied to any type of soil. Okay. So you see the primary use of this apparent to be underpinning work or cut-off wall. It's an environmental application. So type of jet grouting, you can use like a single fluid, you can use double fluid, you can use triple fluid. So single fluid is just only the grout material. And then double fluid is the air and grout material it can inject, and then with high pressure, and then it can rotate. So it will be forming a column of, the soil plus soil plus grout mixture, basically. And then the third one, you see that the air, water, and then the grout material, and it will be rotating and then mixing that also. For injection, so you see how it looks like over here in this. The first you have to make a hole and then inject this the grout material. Over here, you see over the second pictures, the air, water, depending on the system you use. And then finally, it's just bottom and then lift it up. So basically, it will be forming a column like this. Okay. So, again, as a grouting material, sometimes using for underground underpinning. So some of the existing structure is there, and then you have to improve the strength of the foundation soil. So sometimes we just inject grout material to fill that hole and to increase the strength of the soil, the foundation soil. So, but you have to be careful while doing this. If you apply too much pressure, then it will be a problem. So these are that suitability of the grouting methods, and depending on what particle size. You see over here, for gravel, sand, and silts, you see the jet grouting is suitable for any type of soil. This is suitable for all type of soil. Gravel, cement slurry is suitable mainly for the gravel. Okay. Chemical grouting is suitable for gravel and sand. Permeation grouting is obviously, for the gravel and sand, so no pressure. And then compaction grouting is, it can be for sand and hydrofracturing, it can be for sand and clay also, and also for the rock. So again, these are the different technique we already explained earlier. So depending on the particle size, the displacement grout, hypercompactions, all these things you already explained. So admixtures, thermal treatment, reinforcements, and then also chemical grouting over here. Chemical grouting and displacement grouting is basically over here. So the chemical grouting for the gravel and silt, gravel, sand, silt, and displacement grouting can for sand, silt, and clay. So again, groutability of the soil depending on there's a relation with the grout material and the soil particle size. So whether this we need to see the permeability of the soil, you need to see the permeability or viscosity of the grout material, and then find out what is the groutability ratio. Sometimes if whether it is groutable or not, we need to find out from the groutability ratio. So here, permeation grouting, so there are different types of material. It can be resins, it can be silicon or emulsions, bentonite cement, it can be only cements. So different types of material, the permeability, effective soil diameters. So from here, you can find out whether this groutable or not, so that you can find out from the groutability ratio. So I'm going to talk about that. But here you see this is non-groutable, marginal groutable over here, and then this is the for sand to gravel, this is groutable. So depending on the particle size, you can find out. Again, we need to check the properties of the grout material and properties of the soil need to be grouted or improved. So we need to check both properties and find out. So these are again field application of the grout material or for the granular soil. The cement, where you can use the cement, where you can use the clay or bentonite cement with for gel or emulsified bitumen, silicon gel, resin. So there are different situations and what type of soil you can use depending on the permeability of the soil itself. So this will give you a guideline from Xanthakos papers. This table is formed. Application, again, I mentioned earlier, densification of the granular soil, raising settled structures if you apply pressure, so the grout material will lift up the foundation or any structures. Settlement control, underpinning of the existing foundation, excavation support, protection of the existing structures during tunneling, and then also liquefaction mitigation, and then water control. Okay. So again, we will be talking about what are the different types of grout material. So before that, so again, we need to basic rheology. So basically, as I mentioned, so this is not a just only water. So you are injecting water with cement or some other material. So we need to know that what type of fluid and their viscosity. So basically, we need to check most of the time when you mix with the grout, it's not Newtonian fluid, so it will be Brigham body. And then we need to check different viscosity with the shear strength. You see the equation over here, tau is equal to C plus sigma tan phi. So basically that's the shear strength. But here in terms of viscosity is, you see the plastic viscosity, how the plasticity of that, then how it will be flowing. And then depending on the velocity, right? So all these things you need to check. So velocity and the shear stress also is important. And also you need to check the dynamic viscosity, plastic viscosity, apparent viscosity, and the cohesion, all these different parameters you need to check. So, and then from there you decide how much will be the pressure. So again, rheology behavior of the Brigham body for the internal friction. So over here, earlier normal cases for C5 soil, we use the cohesion and angle of inlet friction. Tau is equal to C sigma phi. So over here, gamma d is coming, mu d and dv by dx. So basically, this velocity and the viscosity is coming into the picture. So again, at the bottom, you see here C plus sigma tan phi. So this term is adding over here because of this rheology, because of the viscosity is coming into picture. So how much is the flow, and depending on how much is the shear strength of the material. So this one is, you see that the apparent Newtonian fluid, the apparent viscosity and the plastic viscosity is the same. And this is the viscosity for plastic viscosity and for the Brigham fluid. So what is the apparent viscosity and plastic viscosity for the Newtonian fluid is the same. So basically you need to calculate that what over here, as I mentioned, the shear strength you need to check, and from there you can find out that how much the pressure you need to apply later on. Okay. So here again, that the viscosity and with time with the material, injective time and the setting time you need to check, because you are using cement, right? So if you are using cement is with initial settings time is 30 minutes. So we need to, and how the viscosity is going to change with time. So that's the one you need to check. So it depends on the flowability, right? So if it is too much delay, you cannot pump it or it cannot flow. So injectable time is, you see that 25 to a little bit more than 30 minutes initial set, and then this is the final setting over here, and how the viscosity is going to change. So viscosity is much higher. You see almost 120 the final setting. Initially it was 0, and then around 20. So with time. So this is, you see the initial viscosity of the grout is low and increases gradually until the initial set time. After initial set time, the viscosity increases exponentially. You see, then it will be very difficult to inject. Injection time should be controlled before the initial setting time. So this will give you a guideline how much will be the timing and what time you need to inject. Okay? So depending, again, it depends on the viscosity time graph. So now, what are the different types of grout material? there are two types of grout. One is the suspension grout, and then second one is like a solution grouts. So suspension grouts are made up of solid particles. So basically the soil, cement, lime, asphalt emulsions carried with water. Okay, so the carried with water. So when these suspension are injected into the soil, soil for the purpose of permeating voids that form, relation between the grout particles and the soil void must be considered. So we need to consider that for the suspension grout. Solution grout is there are several types. There may be aqueous solution, there may be colloidal solutions, there may be non-aqueous solutions, there may be emulsion, and it can be combined. So again, so for aqueous solution, it can be silicate derivative, it can be lignosulfate derivative, it can be polyacrylamide. There are different types. Non-synthetic solutions, so synthetic resin and vulcanized oil. So different types of solution grout and suspension grouts are there. And then again, it depends on what type of soil you are going to use it. So grout material, as I mentioned, the selection of the grout material should be considered as mobility, penetrability, cohesion, grid potential, setting time, and solubility. So all these factors you need to check to which material is suitable for a particular site. So there are four grout material, as I mentioned, the particulate, colloidal, and pure solution, and other grout materials. This is the material generally used, and you have seen that the solution and suspension grout, so many different types. So here, the grout materials, so particulate grout, colloidal grout, or solution grout. So you have an idea depending on the viscosity, toxicity, the strength, and relative cost. So all these things you need to check, and then you need to select, and then also you need to select what type of material, and then find out what is the groutability ratio, whether this material is suitable, whether it is groutable or not. Okay, so most of the time, commonly people use the particular metal like a cement 1 type or ultra fine cement, and then water cement to water ratio injected. So that is very common. And it can be colloidal solution, the silicate, it can be solution grout, lignosulfate, polyethylene, polyacrylamide, so all these different types. So this is very important. Groutability ratio is an indication of the injectability of the solid suspension grout in the granular material. So what is that? So basically D15 of the soil. So the soil you are trying to improve, that is D15 from the particle size distribution graph. 15% finer. So, and then D85 is for the grout material itself. Okay. So the D80 particle size, 85% of the soil is finer, particle size of the grout being injected. Okay. So again, so this is, if this ratio D85, D15 of the soil, D85 of the grout should be more than 25. Okay. So it should be more than 25. So then the grouting is possible. If it is less than 11, then the grouting is not possible. So that is very important. You need to check. And obviously, it depends on the particle size and then also what type of grouting you are using. So this will give you a guideline also. The particle size, limit of groutability for cement, for clay, for if you are injecting clay type of material or bentonite or cement, asphalt emulsion, and if you are injecting as a grout material. So this will give you a guideline. So again, basic injection. So as I mentioned, so you have to make a hole into the ground and then inject that grout material, and then you just lift this pipe up, right? So initially more pressure and then the less pressure. So this is the basically you need to find out how much is the quantity of discharge into this area, right? The grout material. So we need to find out, as I mentioned, so we need to know a few things, and then you need to know the velocity. You need to know that how much maximum height, it injected. And then also it depends on the porosity of the soil. So finally, you can calculate how much the grout material really injected into that area. Okay. So the ground is uniform or isotropic. You assume that Newtonian flow injected from the bottom to the pipe and then penetrate to the radius r. So we can find out all these relations. And then also you need to know the permeability that the beta G is the grout to water viscosity ratio. So that is also very important. So we need to know the permeability of the soil. You need to know the permeability of the grout. And these are the viscosity of the material for the different types of material and the concentration of the solid. So this is also another different types of material and the coefficient of permeability. I'm going to go in detail. So again, compaction grouting, what is happening over here? What should be the, you apply pressure and then you add joining because the grout material compact to the nearby soil and basically densify the soils. Okay. So here, depending on, you see here that how much is that the initially, that the compacted soil over here are not, and the grout material is the radius is basically that RP over here, and then how much the area is really controlled. So basically, how much is the lateral pressure applied? So you need to find out from there. Basically that depending on how much the soil is basically the compacted, you can find out from these equations. Hydrofracturing, again, as I mentioned, so this will be applied too much of pressure and fracture the rock. Injection point, you see how the grout material is transported to the fractured rock. Initial stage of grout injection, initiation of fracture, so we applied more pressure. Penetrate the grout into the fracture, low viscosity grout. Penetration of grout into the fracture with high viscosity grout. So depending on situation, you can use this method. Okay, so sometimes this is generally used for the rock. Hydrofracturing. So how much is the pressure you need to apply? So this is the the pressure in the grout. So this is the equation you can use. So you need to know how much is the overburden stress. You need to know how much is the lateral earth pressure. That whatever we studied in soil mechanics, that lateral earth pressure coefficient, that when this that earth pressure at rest or maybe active and passive. In these cases, we'll be using that earth pressure at rest. We need to do that. How much is the overburden stress? And you need to know how much is the cohesion and angle of inflection of the soil and also for the grout material. So you can find out how much application of the pressure. So this is important when you apply pressure. And then when you lift up, the pressure should be less. Okay? So that's the one. So you need to know what equation you need to use. So these are the equations generally you use. Jet flow. So again, we have to go much more detail. So basically, as I mentioned, there are three different systems. It can be air, it can be water, it can be air, water, and system, and also the grout together. So how much should be the distance over here, xc over here for the jet? So you can find out from this equation if it is in air, and d naught is the how much is the diameter. Air and water, so you can find out from what material you are injecting and what system you are using and what pressure you need. So basically all this situation you need to do. So for the jet grouted, so basically it is the core zone you see here, the mixed zone, compressed zone, and the permeated zone, okay, for the sand. So it's very easy. So you can find out. This is for the clay is different. Again, core zone is the center, mixed zone, and the last one is the compressed zone. Because the permeability is so low for clay, so we cannot do that for permeation. So design consideration for grouting, again, we already explained that the groutability ratio. Cement grouting is, again, it should be more than 11. If it is less than, and if it should be more than consistently groutable if it is more than 24. And for the rock is different. You need to find out how much is the width of the fissured rock, and then also instead of D85 is D90 of the grout, okay, 90% finer. So this is for the soil, this is for the rock, the groutability ratio. This is very important whether its grouting is possible or not. For rock, you see it should be groutability it should be more than 2. It's consistently groutable, and when that groutability ratio is more than 5. For soil, it should be more than 24, and consistently groutable it should be more than 11, and it is consistently groutable is more than 24. So again, this will give you a guideline. I'm not going to go in detail here. There are pressure, as I mentioned. So how much is the pressure while injecting the grout, the pressure is very important. So we need to know how much is the pressure. So these are the pressure required depending on the unit of the grout, unit of the water, height of the grout, of the injected point, and height of the groundwater table of the injector. So all these things you need to know. And also the rate of injection grout, all these things you can easily find out from this equation. So again, time to penetrate. So also there is an equation is given by Raffel and Greenwood. So how much time is required? So again, depending on the viscosity of the material. So you can find out from here how much is the penetration radius and how much will be the flow. Again, you need to minimum pressure or gradient, how much you need to overcome the Brigham fluid to use. So again, you need to find out how much is the hydraulic gradient. It depends on how much is the shear strength, how much is the effective diameter, and unit weight of the grout material. So that is very important. And then also the pore diameter, also you need to check how much is the soil permeability, how much is the water viscosity, how much is the porosity of the soil. All these things you need to check. So these are the design parameter you can find out. So this is the soil permeability, depending on the soil permeability, how much is the yield strength, how much is the hydraulic gradient. So also there is a guideline for that. How much is the hydraulic gradient to maintain this flow. So this is what I'm talking about, this minimum hydraulic gradient. You need to maintain that I minimum. And then grout pressure, I already mentioned earlier, the grout pressure. So when you inject it below the ground, the pressure should be high. And then also when you lift it up, the grout pipe, so then the pressure should be low. So over here, the grout pressure, you can find out from here, how much is the unit of the soil, how much is the height, that K0, as I mentioned, this is lateral arc pressure coefficient, and how much is the unit of the angle of infiltration of the soil material. So this is another injection pressure is given by this Chinese ground improvement committee. So they have how much of the grout pressure should be 100 times alpha times P, where alpha is the surcharge factor, how much the below the ground, and then P is the surface surcharge, and then C is the grout pressures, grout sequence factor, gamma, beta M is grouting method factor, lambda is the soil characteristics factor, and H is the depth of penetration of the injection point from the ground surface. So how much at what depth? So then you can calculate how much is the grout pressure. The earlier equation also the same. You can calculate that how much the pressure should be for the grouting pressure. So this is again volume of the grout with the grouting pressures. So I'm not going to go in detail here. Limited penetration radius, how much is the limited grout head? So all these things you need to know. And then injected volume, how much is the volume of the grout material when you inject it? So you can calculate from this equation. So there is a correlation factor. You can find out all this R. You can find out the grout volume from here, and then length of the grout material. So all these things you can find out from here. How much is the injected grout volume? So and then so how much should be the the grout hole pattern and the spacing? The same thing earlier you mentioned, like for sand drain or any other. So grout also, if a huge area, so how your layout of one pattern. So it can be like this one. So it can be like one grout hole over here, and this another one here, another one. It can be like a triangular. It can be square pattern. So and then you need to grout hole pattern and at spacing you can calculate from here also how much should be the width is basically covered. So using these equations, if you know how much is the radius of that the grout hole and how much is the spacing between two, and then you can find out how much is the width is going to cover. So then the grout hole spacing, you have a guideline what type of soil. The soil depth is less than 25 meter. Then the grout hole spacing is 0.8 to 1.3 meter. Sand and gravel is 1 to 2. For gravel is 2 to 4. And then also sand and gravel permeability you need to check, And then for the rock, it is the grout hole spacing 1 to 3. or open cracks is 2 to 4, and different structures. So again, you need to do 3 to 5, or cavity filling, you need to have more because you need really huge quantity of the grout material to fill that hole or cavity or sinkhole. So for the compaction grouting, there are again several equations are there for the grouting. So as in compaction grouting, you apply pressure, you are adjoining the soil nearby, correct? So grout hole spacing you can find out from equations, and you can find out how much the ground is going to heat. So that also you can calculate. And how much is the pressure over here is 700 to 300 kPa, and grout material generally is cement, ordinary Portland cement, and the slump with 25 to 75 millimeters. So it's very liquidy type of material generally used. Then for hydrofracturing grout, so over here, so we apply pressure, and then there is a minor crack. You just inject with high pressure so that the fracture will be filled with the grout material, and then it will be forming a whole soil mass will be stabilized, or rock will be stabilized. So again, the jet grouting we mentioned, you have seen different single, double, and triple, technical capabilities. So mostly the air, water, and the grout material. And then for the gravel, this is single one is good. Clean sand, you can the single, double, or triple. So I'm just again the air, water, and gravel grout material. It can be injected and rotated, and then lift it up. You're mixing forming a soil cement column, or salt, or any other chemicals, forming a column and then go out. So this will give you that what method for what type of soil is more economical for selecting a jet grout. So depending on, as I mentioned, there are 3 methods, so you can select which one is the best. Then jet system, you need to find out how much is the unconfined compressive strength also. So you see unconfined compressive strength 7 to 22, 7 to 20 for double jet, sand and gravels 3 to 14 you see a strength, and for sand and gravel 3 to 10 you see a strength, and this is the column diameter. So basically you see the point, it can be 0.6 to even 2.5 meter, depending on the column diameter. So if you apply too much of pressures, it can make a column of 2.5 meter diameter. So you get a huge column, and you can construct on that type of like a column. Earlier you mentioned like for the lime soil, also you can make a lime column. Same thing, you can make a jet column using jet grouting. You can make a stabilized soil column, okay, and then you can use any type of infrastructure, embankment, or foundation on top of that. Flow rate and of withdrawal and the column diameter. So these are typically in medium dense sand, and typically for the loose clay. So how much should be the column diameter? How much is the rate of withdrawal? So this will give you a little bit of guideline. And the quality control here, following steps. So obviously, when the grouting is done, how you're going to check that? Okay? So evaluate the grouting record, including the grout volume, injection pressure, rate of injection, time of injection. So all these things you need to check. Inspect the integrity of the uniformity of the grouted column or well. Verify the dimension of the grouted column or well, and evaluate the strength of the grouted column. So that is important. How much is the strength of the grouted column? So all these things you need to check. So how are we going to check? So obviously, you need to go to the site and take a core sample of the grouted column or wall to verify how much is the strength. And you can do SPD test, the standard penetration test, or you can do the cone penetration test to find out and how much is the strength gain because of this grout. And then also the single column or composite foundation loading test. So just for example, the plate load test type of stuff, you can do similar way, like a same thing for the pile load test. Same thing also you can do for the stabilized the column, stabilized column using grouting, and then you can apply load on the top of that and see how much the load it can take. And then cross-hole seismic geophysics. So you can use that also to find out the quality. So these are the different, as I mentioned, this is how to check that the quality of the grouted material. Okay, I think that's all up to this. This is up to the grouting now. So any questions? So I need to. So there are a lot of references here, so you can see that where from I have taken this all the material. And so idea is overall summary is basically there are different types of grouting available, and you need to see depending on the particle size, and then also you need to see that the viscosity of the material, not Newtonian flow and Bingham flow. So most of the cases is Bingham flow and the viscosity, apparent viscosity, plastic viscosity, all these different viscosity you need to check. And then depending on the suspension grout or solution grouts, so you need to use what type of grout material, and then also particle size. So mostly jet grouting is suitable for all particle size range, and then also for formation grouting is suitable for gravel and sand. Compaction grouting, you are applying pressure, so you can use for silt and clay, or silt and gravel also. Silt and sand mostly. So you can do that. All right, so I'll stop here now. And so anyone has any questions? I don't know. I mean, we are not going to solve any problem on this grout pressure or how to for any different grout. Most important thing is how much the grout pressure you need to really apply. And there are standard equations that are available, and then you can use that equation depending on the overburden pressure and the viscosity unit weight of the soil. So, and then earth pressure coefficient. So easily you can find out how much the grout. Only thing is when you go below the ground because of the surcharge load, you need to apply more pressure and then just lift it up. As the grouting proceed, just lift it up and forming a the stabilized grout column. All right, so now I should talk about that ground anchor, soil anchor, and then the soil nailing. Okay, so let me share now. So can you see my screen now? Ground anchor?
Yes, sir.
Okay. All right. So I have to go quick. So I'm going to talk about very basic about the ground anchoring system. What is ground anchor? What is the advantage? How to design? I'm not going to go too much of detail of design, but the basic, fundamentals of grouting. And then grouting anchor and the soil nailing is almost a similar type concept, but I'll go quickly and then talk about that soil nail also. So ground anchors, also called the tie back, and which relies on the pre-stressed steel or tendon bonded with the stable mass at greater depth and distance to provide the tensile resistance. So basically, the ground anchor is basically the steel rod. You are inserting into the ground, and then you have to inject some grout material also there. So tensile force is induced by the pre-stress in the steel tendon, provided additional normal stress and critical surface. So the shear strength along the critical slip surface increases, thus resulting the high factor of safety against sliding. So over here. So this is the ground anchor. So brief history is temporary support of excavation system before 1970, but people are using as permanent structures now. Ground anchor is a device to transferring the tensile load to a secure load bearing soil or strata. So we check what type of soil is suitable, this grouting, this anchoring. An anchor is a tri-rod or steel bar or cable or multi-stranded cables having tensile strengths more than 800 meganewton per meter square. So basically, the tie rod is surrounded by cement and some other fixing agents. And basically, it's a steel rod, and we call it that is tandem. And there are different size of steel rod is available. So you see for 26 millimeter to 64 millimeter diameter. Okay. So so basically what you need to do over here, use the deep excavation. So it can be used for deep excavation. It can be used for vertical rock anchor for tying concrete dam with base, anchor in tall installation tower, anchor in dry rock, conventional concrete gravity dam, highway retaining walls, slope stabilizations. There are several applications you can use. So basically, idea is anchor transmit the tensile force to the main structures, okay, to the surrounding soil. So over here, this is like an anchor over here, and then some portion of this over here, this is filled with the grout. So we'll talk more details about that.
Okay. Hello, excuse me, sir.
Okay.
Sir, slides are not moving, sir.
Really? So what you can see now?
Only the first slide, sir, ground anchor.
Oh, really? So this one?
No, sir.
Not moving. So now you can see?
No, sir. Just you can try once.
Shall I just stop share and do it
Yes,
again?
sir. Yes.
Okay. Yeah. Unless someone tell me, I don't know what is going on. Thank you, at least, you know. Can you see now?
Yes, sir. Right now it's
What you can
slide
see?
number 3. It's 2.
So first one, you just see only one. The first slides you have seen, correct? Or
Yes, sir. Yes, sir.
this one you have seen earlier, or
no, sir. First one was on the
so
screen.
only this one?
Yes,
Only
sir.
this one?
Yes, sir.
Oh, okay.
Yes, sir. Only this one was there.
Oh, okay. Yeah, sorry about that, you know. So then I'm just talking myself. So again, the ground anchor is generally, as I mentioned, you know, it started temporary excavation in 1970s. So basically, what you need to do, anchor using a steel rod, basically, and then secure the load, transfer the tensile load to the surrounding soil, basically, or rock. Is a tie rod. It can be, you know, a steel bar. It can be cable. It can be multi-stranded cables having tensile strength should be more than that. And sometimes a steel rod can be, it's called tandem, and then also it has available in different diameters. So 26 millimeter to, you know, 64 millimeter. So it can be used for different applications. Deep excavation. Can you see the slide now?
Yes, sir. Yes, sir.
Yeah, different uses of ground anchor, correct?
Yeah, yes, sir. Yes.
Okay, good. Deep excavation, it can be used the vertical rock anchor, trying concrete dam base. So sometimes the uplift pressure, so you can do that. Anchor of trawl installation, tower line, anchor in dry dock, high retaining walls, slope stabilizations, uplift pressure, all these things. So basically, anchor transmit the tensile force to the main structures in the surrounding soil. Okay. So that's become a substructure itself. So like this example is over here, the vertical, the concrete dam. So you can use the anchor over here, so it will not topple. Same thing for the tall tower. You can do the anchoring. You can do the anchor for the dry dock so that it can resist the hydraulic pressure or hydraulic head. So these are different example. Also, the concrete gravity dam, ground anchors, and the anchor system over for the slope stabilization. So you can see the stabilize the slope. You can see the high retaining wall using this anchor. And then, so basically you just insert a steel rod into the soil or rock, and then make a hole first, and then insert the steel rod and then inject grout. So that's how, and then, so this is a temporary excavation, and it can be used for the permanent also. So uplift slab, so I already mentioned that. So benefits of this, the anchored wall compared to the gravity wall, just for example, unobstructed workspace for excavation, ability to withstand relatively large horizontal pressure without requiring significant increase in the wall cross. So we'll talk more detail in the retaining wall design. MSC wall eliminates the need of selected backfill. So you just don't need to backfill, eliminates the need for deep foundation support, and reduce construction time. So these are the few things you need to. So here, general features of the anchors. So you see over here, so at the center, there is a steel rod or tendon. Okay, the center is a steel rod. And then there are some portion you see the anchor bond length, and that is the tandem bond length, and the front part is called that unbonded bond length. Okay, and then so inside there is a centralizer. So centralizer generally used to that the steel pipe should be at the center of the hole, and then you see at the bottom you see this is the anchor grout. So you just inject the grout material. So this is the anchor diameter. So this is with the grout material. This portion is called the fixed grout, and this portion is called the free grout. So later on you'll see that, and then and on the top there is an anchor head, and there is a bearing plate, and the bearing plate is attached to it with the nut and screw. Okay, anchor nut and bolts. So this is overall things. So idea is when you inject when you anchor a steel rod into the soil or ground, there should be some critical failure surface, and then this portion of this bonded length should be into that beyond that active zone. So we'll see that. So this is anchor component or plate bar. So this is, as I mentioned, the tendon, and then the bearing plate and the anchor nut on the top. And advantage: no obstruction for workspace during excavation. Tolerable to large lateral pressure without significant increase in the wall cross section. Used for temporary excavation. No need to have selected backfill. I mentioned earlier, fast construction and less surface right of way issue. Limitation: obviously, the ground anchor may be limited to object in the ground, such as underground tunnel or utility. So when you inject the ground, so obviously this rod is there, so you cannot use that underground space. Okay, or ground right of way space. So they may not work well for the soft soil due to large and creep deformation. So it should be, you cannot use for very soft soil. So it can hold, for the bond stage should be quite good so that it can hold. Otherwise, that will come out, the steel rod, because of the tensile failure and the bond stress. So we'll talk about that. And the difficulty may arise in construction watertight connections at the anchor's structural slab interface below the groundwater table. So if it is a groundwater table, below the groundwater table is not good, this anchoring method. So there are different 4 types of ground anchor generally commonly used. One is like the straight type A, type B, type C, and type D. Type A is the straight shaft gravity grouted. So first you just make a hole, insert the steel rod or tendon, and then gravity, just only with gravity that the grout material will flow, just like a permeation grouting earlier. So here, so this is the bonding here over here. This is the bonding stress. The tensile stress will be transferred to this soil over here. Okay. Then the pressure grouted. So pressure grouted is we apply a little bit of more pressure. So you see over here, whatever the grout height, the grout hole, and a little bit more. Okay, a little bit more, it is compacted. Okay, just like a compaction grouting over there. The post grouted. So over here, this one you have to do one grouting material, inject the grout, and then give some time gap, and then apply a little bit more pressure, and then grout it. So then you will get this type of post-grouted anchor. And then also the under-ringed one. You see there is a groove over here. So there is a special type of material. You can make a hole like that. And then similar type of concept like when you do like underneath pile construction. So there is a system, you can just press it, it can go on the side and then make a hole, and then it can squeeze into the original hole. So that's why this underneath situation, and apply more pressure over there. The ground material go into that. What type of material that the 4 methods? So what type A, this is suitable typically instead of rock and stiff or hard cohesive soil. Type B, coarse grained soil or weak fissured rock can be used, and also for the fine grained cohesive soil. The pressure over here is 0.3 megapascal, 0.35 megapascal. Then type C for the post grouted. So again, high pressure grout fracture, initially grouted in the wedge outward with the soil to enlarging the grout body. Then under-rimmed one is used to farm to hard cohesive deposits. So these are the different methods or different types you can use it. So how the load transfer mechanism, this is very important. So you see here, this is just for example for sheet pile wall, or you need to stabilize this slope over here, just for example. So what did you do? Basically, you just insert this tendon, and then it's a bearing plate and nuts, as I mentioned. And this is the grout material injected over here. This portion is not grouted, but sometimes you use a very thin grout. This is the active zone, and this is the critical failure surface over here. How the bond strength, bond length, obviously, if it is failed, it is coming out, then the purpose is not solved. So if it's the bond shear strength is go on increasing, and then ultimate bond strength will be, and this is the stable zone. So there is an active zone, this is the stable zones over here, and this is a critical surface over here. So this is another pictures over here. This is the active zone, and this is the passive pressures. And then when you design an anchor, so you need to know how much is the height, how much is the depth of penetration of the sheet pile, just for example, and then you anchor it. And then obviously when you do this, the grouting part, it should be beyond this failure line, okay, beyond this failure line. And then otherwise it will not be stable. If this zone is within this active zone, this is not going to solve the purpose. And then there is an equation also for that, at how much should be the value of psi, or so here it's much more detailed. So here there is one anchor, this is second anchor. So you need to, while designing, you need to know how much will be the spacing, how much will be the length of this, so all these things you need to know. And then most of the time the anchor can be horizontal, anchored in horizontal. It can be and at certain inclinations. So certain inclination is most common. And then also these will give you a design guidelines. If it is H, you see the minimum unbonded length is 3 meter bar, or 4.5 meter of strand. So that is, so over here, if it is the ground level is here, so it should be at least 4.5 meter over here, like that. And this xi over here, you can 1.5 meter minimum, or 1.5 meter, or 0.2 times the height of this, sheet pile up to the penetration depth. Up to what portion of the sheet pile is inserted into the ground. So you need to check that all these different parameters for while designing this. Okay. So as I mentioned, it can be horizontal, it can be inclined certain angle, and then you need to know how much is the horizontal spacing, how much is the vertical spacing. All these different parameters you need to know. And again, how to design it. So you need to know how much the pressure distribution is coming, and then depending on the soil type, it can be whether it is single anchor or double anchor. The pressure distribution of the soil, it can be trapezium, it can be rectangle, it can be triangular. So all these different things will come into pictures depending on the soil type and how much the lateral pressure is acting on this sheet pile wall. So you see over here, grout anchor and the stability. So over here, the active zone, and this is the minimum distance from the wall to stand the anchor bond length. So this is very important. And then the active zone over here, and this is the deepest envelope, deepest point of potential failure mechanism, which requires some anchor force to stabilize. Okay. So basically, the bonding length should be beyond that failure length. So that's one you need to remember. So again, main anchor is divided into two. One is the fixed length and the free length. So this is the fixed length over here. This is the primary grout is there. And free length was the secondary grout. And the tendon is the steel rod that is at the center of this hole. And that is taking the tensile strength. Okay. Because the soil cannot take the tension. That's the reason we are using steel to take the tensile force. It can be vertical anchor. So again, the free anchor, fixed anchor, primary grout, secondary grout, and the tensile force. And there's a slab, means there's a plate and the bearing plate and the nuts. Okay. So the bottom place, the lower place is the bottom or lower part of the anchor over which the tensile force is transmitted to the surrounding soil. Soil is the fixed length or bond length. That is the most important. Okay. Fixed length generally is used a thick grout material, and the free length used like a thin grout material, or you can say secondary grout. So again, I'm not going to go in detail. So again, like as you mentioned, the permeation grout, the pressure grout, all these different types of material. Also A, B, C, D, we mentioned the same thing, what is going to happen over here in anchor. I'm not going to go in detail here. Unbounded length. So how to installation of the ground anchor? So first you make a hole. It's very simple. First you make a hole, drill hole. And then hole can be either vertical or inclined. Okay. And most of the time is inclined. And then, and depending on the soil, it can be with casing or without casing. And then the anchor tandem is inserted centrally at the hole, and then use the centralizer so that the steel rod should be at the center. And then inject the grout. The grout generally use cement is pumped into the space between the tendon and the hole with the predetermined grout pressure. Pressure may vary the primary grout and secondary grout. Primary grout pressure should be more. Secondary grout pressure is less on the fixed one, and then free part. And if the casing pipe is used for drill shop, it should be withdrawn before grouting. Obviously, if you are using casing for making a hole, it should not collapse, right? So when you inject the grout, obviously you need to take out the casing. Okay. And the grout is finally allowed to cure because the cement you need setting time, so 3 to 7 days. And then when the grouting is done, they need to do the test. So that's the reason reaction jacking or locking system called the anchor head to install anchor at the ground surface on the structural surface, on the top surface. And then tensile strength is applied to anchor by hydraulic jack. And then these values varies from 1.25 to 2 times the design load. Okay. So that, and then when the load is applied to the anchor, the lock-off system is engaged and the applied tension from the jack is released. So this is how the construction process. So design of Conquer soil anchor. It's a type of anchor system we mentioned, type of soil type and type of soil pressure. So all these things, type of the grout, and grout pressure. So these are the different types, ultimate load capacity, and how much is the fixed length. That is the most important length is important. And that is the tensile strength is distributed basically in the fixed strength of the grout material of this anchor, that area. So this will give you a guideline of ultimate load bearing capacity and the fixed length. How much is the fixed length depending on what type of soil, whether it's sandy soil, sandy gravel soil, or medium and coarse gravel, medium to coarse sand, or fine to medium sand. So depending on that, you can easily find out how much is the ultimate capacity. So as I mentioned, over here is the steel rod. This is the anchor. So how much should be the diameter of the grout hole, or then that how much should be the spacing from the ground level, at least 4.5 meter. And then also how much should be the spacing between these two, that is also important. And then also that the grout length, the fixed length should be at least 3 meter minimum, so that it can transmit the whole tensile load to the surrounding soil. So this will give you a guideline. So now the thing is, how much is the width of the anchor? So this is the width of the anchor B, correct? Width of the anchor or width of diameter of the hole, basically, width of the anchor. So how to find out the width of the anchor? So this is how much is the volume of the grout and how much is the actual bond length or fixed length. So you know that how much is the fixed length and then the free length, right? Fixed length and the free length, right? So primary grout and the secondary grout. So you can find out how much is the width of the anchor using how much is the volume is of the grout divided by square root of that divided by 0.78 times L naught, where the actual bond length or actual bond length is L naught. So here you can find out if you know that the load carrying capacity QU, and if you know that the anchor capacity withstand, how much is the initial pressure, so you can find out the factor of safety from there. So you can calculate how much is the allowable load, so how much is the ultimate load divided by factor of safety. So now this is the how you can find out this PU, the ultimate load over here, this PU anchor load capacity. So you can find out that L naught tan phi times B time naught. So easily you can calculate where P naught is the vertical overburden stress, and it should be at least the factor should be at least the Q ultimate should be 1.5 times L naught tan phi times B times P naught. So easily you can calculate how much is the ultimate load. And then now if the anchor is in cohesive soil and if the anchor is in sandy type soil, also if it is under rim circular anchor or straight circular anchor, how to find out the ultimate capacity. So and then what should be the bond strength between this and the surrounding soil. So that there is a standard table is available. So easily you can find out how much is the ultimate capacity for anchored in cohesive soil. Okay. So just for example, if it is a straight or under rim, if it is an under rimmed one, you can use that ultimate capacity using this equation, where is the under rim diameter capital D, where small d is the shaft diameter, and then NC is the bearing capacity factor, and then it is for mostly this is for clay, so that's why this bearing capacity phi is equal to 0, and that's why this value is N. And you can calculate this using this equation, the ultimate capacity. And then for straight anchor, you can use this using this equation to pi times D times L naught. This is the fixed bond length, fixed anchor length. That is the most important. And then SB is that the soil to grout bond. So soil to grout bond. So this is most important. That is the standard values are available. How much is the soil, the bond strength? So if you know that, you can find out the ultimate capacity for the straight anchor. As I mentioned, that ASB you can find out from this table. So depending on the diameter and the typical grout pressure and then the friction. So this is the soil anchor and the suitable soil for anchorage. And then also I'm just going to go over here, high pressure grout and small pressure grout. But I'm just going to talk about this one over here. How much is the bond strength, as I mentioned, for the cohesive soil, depending on the type of soil and SPT value, and then we can find out the bond strength. If you know this SB, the bond strength, and then easily you can find out how much is the ultimate capacity for it is under rimmed or straight, okay, for cohesive soil. So now here, this is the possible failure mode. So idea is the tensile failure in the tendon. So idea is when there is a steel plate, a steel rod itself fell, then what is the purpose of using this? So then that is not good. Then pull out failure. Sometimes, it just because the bonding stress is not enough, so it may pull out. So that is not good. So again, the pull out failure, a tendon or grout bond. So then this is a situation like that. Failure of the wall of bending. So again, the sheet pile wall, it bends like that. So that is not good. Failure of the wall due to insufficient passive capacity. Again, it is not inserted with that, the sheet pile. So that is not good. It can be rotation failure. It can be insufficient axial capacity. It can be failure by overturning over here. It can be failure by sliding. It can be failure by rotational failure. So these are different types of failure of the anchor system. So I'm not going to go in detail arc pressure. So again, this is the one, the typical cross section. We have seen this figure. This is the one, actually, this is the primary grout or fixed length. This is free length, is the imaginary, the line of failure, active zone. So the bonding stress, the bond length should be beyond that active zone. And then also it should be minimum overburden cover should be 4.5 meter minimum length, minimum depth. And then, and this angle over here, this 45 degree plus pi by 2, the pi is basically the angle of reach of the material over here. Okay. And then obviously the unbonded length should be minimum 4.5 meter. Okay. So typical diameter should be smaller than 150 millimeter. And then, typical hole of the diameter approximately 300 millimeter. Okay. So drill hole for the anchor is typically 150. So depending on the situation, how you are designing it. Okay. So these are several values you need to check. Anchor length, total length, the anchor ranges from 8 meter to 9 meter to 18 meter. As I mentioned already, underbonded length should be at least 4.5 meter, distance of greater of 1.5 meter or h/5 design length, and should be overburden cover at least 4.5 meter, we mentioned already. Anchor bond length should be 4 meter to 12 meter, and the anchor bond length in rock should be 3 to 10 meters. So these are the guidelines. And inclination angles, as I mentioned, it can be vertical, it can be horizontal, but most of the time it is inclined at certain angle, and that is 10 to 45 degree angle, ranging from, again, commonly used 15 to 30 degree below the horizontal directions. Horizontal spacing, again, while you're designing it, you need to assume some spacing, and then you can design your anchor. So we need to do the horizontal spacing, also do the vertical spacing. So horizontal spacing should be 1.5 meter, the minimum, and the typical design load should be, again, 260 to 1,600, 1,160 kilonewton. So again, what type of soil? I'm not going to go in detail about earth pressure for different ground anchors. So whether it is single anchor, with multiple anchor, how to find out the pressure, again, using these lateral earth pressure theories. And there are different equations. We can use wall with one level of ground anchor, wall with multiple level of ground anchor, how much will be the pressure distribution. And from there, you can find out the bond length and the bond stresses from this equation. So again, this is for the earth pressure in sand. This is for the earth pressure in clay. Again, with only one anchor, it can be multiple anchors. So how to calculate the pressure from using this lateral earth pressure theory. Sometimes if the earth pressure is in the soft to medium clay, then this is the anchor. This is the Ka. You can find out this is a trapezium type of stuff. You can calculate that so basically from here, the pressure distribution, you can calculate how much the pressure is coming into that the anchor, and how much the pressure that the anchor can take. Okay. So there are two types of method, again, the anchor load of a single anchor or multiple anchors. So it can be, you can use these equations over here, tributary area methods. You can use the hinge method, the two different methods to find out how much is the capacity or how much is the tensile force. So you can, any of these two methods you can use. This is for the single anchor. This one is for the multiple anchors. Again, two methods. You use tributary area method. You can use the hinge method. So to calculate how much is the tensile force. And again, you need to know what type of pressure distribution or what type of soil is there. So that is important. And then for anchor load, you can find out from here, and based on the spacing and the total anchor load, you can calculate horizontal shingle anchor, how much is the load you can calculate. And then finally, you can calculate the bond capacity. Earlier, you have seen that for sandy type soil or for clay type of soil, how much is the anchor capacity, you can find out from this equation. If you know the diameter of the hole, if you know that anchor bond stress, if you know that the anchor bond length, so how much is the fixed length basically, and you can calculate how much is the capacity, bond capacity. Okay, I already explained that earlier. So this is how we calculate for two different type of soil. So this is the equation, and then also the ultimate bond strength also can be find out from this table. For the different type of soil, what type of pressure you need to apply. Okay. So this is for the cohesive soil, and then also this is the table for the cohesionless soil or sandy type soil. How much is the ultimate bond strength? Okay. As I mentioned, this is not suitable for really loose soil, or if the soil is pure clay or water table is very high. So we cannot use this method for anchor. So again, if it is a rock, then it's a different ultimate bond strength. You can find out from here for obviously the granite type of rock, granite or basalt or dolomite, the bond strength is more. And then obviously whether sandstone and soft shells, the bond strength is less. So basically, the anchor is anchored into that what type of soil? Is it this rock or soil? So obviously, if there's an ultimate bond strength is more there, if that type of rock is there, right? Or the good soil is there. So I'm not going to go over here, tensile strength, piston stress. I'm not going to go here. There are a lot of guidelines and stuff. I'm going to go here. And then also because it's steel, sometimes we need to protect that for the corrosion protection requirement. Sometimes we use that like a high density polyethylene or polyethylene sheet just to protect that the steel rod or tendon. And also sometimes use some grout also do good to protect. And then also sometimes use an epoxy also. Facing wall, I'm not going to go here. So basically you see here, while designing this, you need to find out all this imaginary plane, and then finally aim is find out the factor of safety depending on this failure plane. And then you see this case A over here. I mean, that is not good because it should be beyond this failure length. So that is not good. And then case B is okay, still not okay. It should be that the fixed length should be beyond that failure line. Okay, so we have to do few trial and error to find out. Okay. And then the base stability, the bearing capacity failure due to the base excavation should be performed. And the same approach of the presented the best stability for the excavation pit. So you can use that. And then also you need to find out if it is anchored in the clay type of soil or very soft soil, then it is difficult. So we need to soil may have creep. We need to find out that in this soil conservative anchor design load and working bond stress value should be used for the permanent anchor. So this is not a good option. Maintaining the wall movement, again, you need to check that. So I'm just going to go over here. The settlement of the depth of excavation and the distance for the excavation, or what type of soil it is there. So you can check that how much is the depth of excavation and how much is the settlement. So you can find out from this graph. Construction, you already mentioned that you just make a drill hole, insert the tendon steel rod, installing the trumpet on anchor, and then grout, insert the grout, and then testing the stressed or pre-stressed grout anchor, the lock off, and the cutting tendon protrusion. So, and then the quality, as I mentioned earlier, also the quality control assurance. So you need to do inspection and verification prior to installation, pre-stressing of the steel rod bar, anchorage or trumpet, spacers. You need to check centralizers so that the steel rod should be at the center of this hole. And then also you need to know what type of the grout material you're using, the bearing plate, and then also use that the corrosion protector material. Recording during grouting. So also you need to check the type of mixer used, water to cement ratio, type of additives you are using. If you are injecting, so maybe you need to use some retarder so that it will not settle quickly, and also check the viscosity. Grout pressure is important. Type of cement is important. strength of samples, sample test, strength test of sample you need to do, and then also the volume of first and second stage grout. So again, into that, the volume of grout, you mentioned that how to calculate if you know the width of the hole, and then also the first part is the free length, so you can also calculate how much is the volume of that grout in that stage. Okay. So typically grout should require the strength is 20 to 30 megapascal in 7 to 10 days. Okay? And then load testing test. So test load is generally 125 to 155 the design load of the anchor. So that's what you need to do. And acceptance or rejection criteria anchor relies on the result of 3 tests. Performance test you do, proof test you do, and the extended creep test you do. For the creep, because creep is a time-dependent phenomena, and for clay type of soil is happens, so you need to do that test also for the creep test for the long time. Okay, and so it's almost done now. So performance test of the anchor again, performance test. You can test involves several load cycle, increasing magnitude until the test load. So load increasing until the design load. After each load cycle, check the elastic and residual deformation of the anchor are recorded. Test load, so at least hold 10 minutes to evaluate the time-dependent deformation for the creep. And this test is to verify the anchor capacity to establish load deformation behavior. And then the proof of anchor test, the proof test applies to several incremental load. So you need to do, and then for 10 minutes before unloading, the initial alignment load, and also examine whether the test anchor is acceptable with the applications. Okay? And then obviously, as I mentioned, so if it is a creep, so then you need to do at least the test for 8 hours, and then also test done for cohesive soil more than plasticity is more than 20, or liquid humidity is more than 50. So that's all for this ground anchor. So if you want to design a ground anchor, so you need to, as a guideline, as I mentioned, so depending on whether this the ground anchor is inserted or in what type of soil, you need to know the pressure distribution diagram. You need to design for single anchor or multiple anchor. What should be the spacing? What should be the length? You need to find out the volume of grout. You need to find out that the fixed length, that is the most important, where this is the one the load is transferred, tensile load transferred to the surrounding soil. And then also the free length, and then you need to do the different tests. And obviously you need to know that the grout material and used, and then also all these strength tests you need to do. Okay. I think that's all for this, the ground anchor. I think I'll go to the next topic is like a soil nailing. And the soil nailing is almost the same type, so I'll go quickly. So, and then there are different softwares, there are different methods also for soil nailing. So I'm going to talk about that. This is little bit almost similar type, but a little bit different. And there are different methods also to install this soil nail. Okay, I'll just stop here.
There is one query in the chat box.
Okay, what is that?
So how to predict life of soil nailing?
Oh, I'm going to talk about this. So this is a ground anchor. So I'm going to talk about soil nail now. Okay.
Okay. Okay.
Okay. So, and the regression is helpful. So yeah, obviously all these things you need to do field test. And if you are doing trial test in soil nailing, so you can find out also from there. So now I have, how much time I have now for this?
Sir, right now it's
8 o'clock, right?
8:03, yes, sir. So we
So
can
now
take 10 to 15 minutes break, sir. After that,
so now 15 minutes break now.
okay, sir. Or as you, as per yours.
Whatever you think, I'm fine. Or
So we'll start from the 8:15.
8:15.
Yes, sir.
10 minutes basically, right?
Yes, sir. After 10 or 12 minutes.
Okay. All right then.
Okay, sir.
Recording stop.
This is the first time I'm doing this.
Recording in progress.
So we
All
can
right.
start now, sir.
Huh?
You can start.
Can you see the slides now?
Yes, sir. Yes, sir.
Call Lily. Let me
Right.
see whether it is going advancing or not. Is it advancing now?
Yeah.
Yes, sir. Yes, sir.
Picture. Okay, good. All right. Again, welcome back. So the ground anchor and the soil nailing is almost the similar type, a little bit of difference. Construction method is a little bit different. And then also there are different types of soil nailing methods are there. And then finally what you do, basically the soil nail, and then on the front face of any stabilized wall, so put some shotcrete, basically, and the wire mesh, and then put a cement and that shotcrete concrete, basically, generally for the facing wall. The soil nail is a technology first used in France for the soft rock. And so again, the project is undertaken in 1961. And basically the first is steel nails are used. And also the first soil nail, also the modern soil nailing, also near Versailles also in France. So basically include high density grouted soil nail with 60 feet long for this, and facing wall reinforced concrete. So this is the history of that. So this is how it looks like after this nailing is done, and then just put a wire mesh, and then put a shotcrete, basically. So how it looks like, so reinforced shotcrete and facing wall. So basically this is the soil nail, and there's a spacing between the soil nail and the drainage layer, and how it looks like for soil nail system, wall system. This is how it looks like also. Is in the top, you can see the soil nail and this anchor plate, and then nut and bolt on the top. The soil nailing is a procedure of reinforcing, basically or strengthening the ground adjacent to the excavation by installing closely placed steel bar or nails. Okay, and as construction proceeds from top down. So this is a little bit different, as I mentioned. So this is from top to down, and it is effective and economical method of constructing retaining wall for excavation support of the cart hill, bridge apartment, and highways. And this process is effectively in cohesive soil, broken rock, shale, and fixed. So this process, whatever soil is suitable. Soil nail applications, as I mentioned, the stabilized or railroad or highway cut slopes, tunnel portal of steep or unstable stratified slopes, stabilizing steep cutting development space, existing over steep embankments, you can use that. Soil nailing through existing concrete or masonry structures of failing retaining wall or bridge apartment to provide long-term stability. So it can be used for temporary, it can be used for permanent. So depending on the situation, different application of the soil nail. Suitability, soil nailing, steep to hard, fine-grained soil. If it's a soft soil, it's not good. Dense to very dense granular soil with some apparent cohesion, weathered rock with no weak plains, glacial soils, and ground that can support or unsupported or vertical cut of 1:2 meter on 1 or 2 days, 1 or 2 days. So you just cut this slope, and if it is collapsed, then it is not good. So unfavorable conditions when the soil is dry, poorly graded, cohesionless soils, that is the good option. Soil with high groundwater table, also not good options. Soil with large boulder and cobble, so it is difficult to insert the steel rod or nails. Soft to very soft fine-grained soil is not possible. Organic soil is not possible. Highly weathered, highly corrosive soil, because the steel is going to corrode, or high groundwater table is there, so it's not possible. So these are the few situations where the soil condition, which one is not possible. The soil nail, so basically what is in situ reinforcing, in situ, go to the site and then do it. So reinforcing soil while they excavated from top down. Okay, this mass is reinforcement reinforced soil function to retain to less stable material behind it. The right soil condition, soil layering is rapid, is a very quick and economical means. In many applications, soil layering can at least disruptive way to construct a retaining wall. And the soil layering requires unusual amount of handwork, craftsmen, and usual work of geotechnical knowledge to construct. So here, how it looks like, the main typical section of soil nail. So earlier, this is a center. At the center, you see there's a drill hole first, and then insert this the nail, okay, and then inject the grout. This is a similar type as I mentioned. So it's inject the grout material, and there is a centralizer. Centralizer is basically that the nail will be at the center, so that when grout materials, all the nail will be covered inside the grout, and then there is, as I mentioned, steel bar, centralizer, grout, drill hole, and then on the top you see over here the bearing plate, and then bearing nut and bevel washer, and then also there is a headed star. Okay, headed star. So these are the few exact, almost similar. Earlier it was like a anchor. It was a fixed length and free length. Fixed length was a thicker than more grout and thin. So it is here. It is uniform. That is the difference. There are different types of nails that are available. So one is the driven nails, one is the grouted nails, one is the corrosion protected nails, one is the jet grouted nails, and the lounge nail. There are different types of nails. There are different specifications. What should be the diameter? What should be the strength of that? Most of the time, depending on the requirements, the company they will provide all the provide with all the data. How much is the tensile strength of the steel nail? How much will be the diameter? There are standard size of diameter is available. So driven nail is generally small nails, diameter 15 to 46 millimeter, limited length, so it's 20 meter length, made from mild steel that are closely spaced. Sometimes if you have a smaller length, so you can just weld it, or there is a spacer, you can attach it and then extend. Grouted nail, it is the bar diameter ranging from 15 to 46, again, stronger than driven nails. That strength is about 60 ksi. And grouted nails are inserted in the borehole of 10 to 15 centimeter, then cement grouted. Okay. And the reaped bar are generally used to increase the adhesion. So basically, instead of just like a taut steel, instead of mild steel, it's more reaped bar. Then the corrosion protected nails. So obviously, this is for aggressive soil, permanent structures. You can use that corrosion protected nails. Jet grouted nail is a composite grout, soil and central steel rod up to 40 meter thick. So again, the jet grouted nail. Lounge nails between 25 to 30, it's a smaller one diameter, and then 6 meter long, are fired directly into the soil, just with a compressed air launcher. So it's just boom, boom, just launch it and then stabilize the mostly it is used for the slope stabilization technique. Okay. So these are the different properties of the nail. So the steel reinforcing bar used for the soil nail, commonly threaded, and maybe either solid and hollow. Most of the time is solid. Bars are generally nominal strength of 425 megapascal to 522 megapascal. Commonly in US, soil nails are used for solid bar, as I mentioned. So with tensile strength of 665 megapascal, and it can go up to 1035 megapascal. Threaded bar, typically nail available different diameters and length approximate 18 meter. Bars also having a diameter smaller than 25 should not be used, if it's just too small. And as I mentioned, so you needed a coupler to extend the length of this if it is more than 18 meter. So you need to have a coupler, and then you can use that, increase the length. Nail head, these are the different properties. Also, you need to check two main components is a bearing plate, and then hex nut and the washer and the headed star. Is almost similar like a ground anchor. Bearing plate should be made with a steel and then typically square, and the grade of the steel should be 250 MPa. And purpose of the bearing plate to distribute the force at the nail end to the temporary shortcut and facing wall. So that's the idea of using this plate. Beveled washer then placed, and the nail bar is secured to the hex nut. The washer nut should be grade consistent with that of the nail bar community. So again, strength is almost that same range. And head start connection may consist of 4 head start and welded near the 4 corner of the bearing plate to provide anchorage of the soil nail head for the permanent facing. So basically, after nail is done, and then put a steel mesh, and then put the shotcrete basically. Centralizer, how it looks like, is a PVC, made of PVC. So centralizer is a steel bar and then PVC, so that the bar will be at the center of the hole. Okay. There should be a regular interval. Typically, it should not exceed 2.8 meter. So it should be, every 2.5 meter, you need to have a centralizer. And along the length of the nail and distance about 0.5 meter from each end of the nail. Okay, this is how you do the centralizer. The grout, inject the grout, right? So you can inject the neat cement grout, basically only the cement and water. And then it can be used for type 1, type 2, type 3, different type of cement can be used. And the water to cement ratio, it can be 0.4 to 0.5. Okay, in some cases, stiffer grout with a slump of order of 30 millimeter can be used. So these are occasionally the stiff consistent. Sometimes, because a lot of centralizer, if the grout material is very stiff, so then that may cause difficulty and installation of the centralizer be difficult. So then ultimate bond strength. The characteristics of grout have strong influence on the ultimate bond strength of the grout interface. We just check the strength after 28 days. It should be 221 megapascal or 3000 psi. Typically, improved workability of the grout due to plasticizer can be extended for 1 hour. So basically, this is a cement grout, correct? Cement is initial setting time is 30 minutes. So sometimes we add some stabilizer so that it delays the setting time. Okay. So, and then how it looks like, the grout pipe is typically heavy duty plastic tubing, varies from 9.5 to 19 millimeter outside diameter. And grout injected smooth and continuously, and between the space of the drill hole and the nail bar, filled with completely with no void space. And then when the grouting is done, so finally you see over here, there is a using the streamy pipe. So obviously you need to do that. And so basically the grout injection is using the streamy method, the grout pipe, which is previously inserted at the bottom of the drill hole until the grout is completely filled. Okay. Then this is how it looks like, the nail bar. Okay. This is high density polyethylene cover. Sometimes you just put it, the nail bar, you just put a cover of high density polyethylene material so that it protects from the corrosion. This is how we do the construction basically. Step 1, excavate a small cut, then make a hole using the drilling rig, and then third, installation of the nail. First you insert the nail and fill it with grout. When the grout is done, then you put the bearing plate on the top and then the shotcrete on the top basically. Okay. So then repeat the same process. As I mentioned, just 1, 2, 3, 4, 5. So it is from the top down. So 1, 2, 3, 4. This is 4 nails over here. And then you have a plate on the top. You see here, plate on the top and nuts, over there. And then there is a drainage layer. Also, there should be a shotcrete on the top. Then this is the final facing or permanent wall, how it looks like. Okay. This is just most of the time when you design any soil nail, so you need to go to the site and see the plan, how many nails you need to stabilize the slope. This is a project I was involved here in Illinois. we have a national forest, Shawnee National Forest, and to how to stabilize the rockfall. Basically, this is the plan used, and these are the different nail size, proposed nail size, and this is how it looks like. Actual site is quite a steep slope, and so basically these are the different points over here. That inject this the grout. So how it looks like, I mean, this is closer view of soil nail inspection later on, and then also that nail insertion into the ground slope ground, basically. This is how it looks like, the soil nails, and this is centralizer. You see the centralizer over here, so that it can be at the center, closer view. Then this is how they do. Basically, they use a mixture in agitator in that grouting method we already explained. The same thing you can see it over here. It's basically they're using ordinary Portland cement in this project. So, and then they use this, if there is in a cement, there is a lump or anything, that can be, discarded. And then mix it over there, and then they pump it to the nail, and then this is the test of nails after the installation. So this is how they test the nail, the load test after 7 days or 5 days. And then so basically that's how we have seen that actual project, how the nail is installed and stuff. Advantages of soil nail is with the right soil and site condition, rapid and economical means of construction are retaining support structure, retaining wall, shorter drill hole, smaller diameter bar for short length, retaining wall are secured laterally into the soil, eliminated piles and foundation footers. Grouting only once is required, saving time and labor, and its technique is flexible and easily modified. Creates less noise and traffic obstruction, less impact on the nearby properties, allowable in situ strengthening of existing slopes with the minimum excavation, allow excellent working space in front of the excavation face, can be used for the strengthening either natural slope, natural or man-made cut slope. So you can use for anything. Obviously, every method has some advantage and disadvantages. These are the disadvantages. So nail encroachment to the retaining ground, rendering unusable underground surface. So we cannot use that. The nail is there. So same thing for ground anchor also. We cannot use the underground space. Generally, larger lateral strain during removal of the lateral support or ground surface cracking may appear. Tendency of high ground soil due to drilling technique, particularly for the coarse grained soil, less suitable for the coarse grained soil or soft clay soil, and suitable for excavation above the groundwater. The water table is there, so then it's not good. This is how using the rotary drilling method. So how we're drilling it, and then insert the nail, and then the grout it. Temporary wall facing construction. So again, temporary wall facing soil nail application usually for constructed using shotcrete. As I mentioned, it's just like a cement and sand, only cement and sand slurry. And thickness of the temporary shotcrete facing wall is between 75 to 10 millimeter, 100 millimeters, so 3 to 4 inches. Shotcrete provides the continuous support of the layer over the excavated face and can also serve fill voids and gaps using different fiber or geotextiles reinforcement. So how it looks like? So it looks like here, like the nails, you cannot see the nails. The nails are there, several nails, and then you put a steel mesh and then put a shotcrete using this with high pressure cement and sand, basically. Type of shotcrete method using dry method or wet method. So dry method, aggregates and sand. Aggregates, less percentage of aggregates. Cements are blended dry fed to the shotcrete ground, depending on the features. So we can use that to most significantly determine shotcrete quality and durability of the cement. So we need to check that. And for a high cement factor, usually 350 to 400 kg per cement per meter cube is generally used. So more cement is generally used for the durability. Then steel bar reinforced was added to the shotcrete as a part of wet mix, increased ductility, toughness, and impact resistance. And fiber tends to reduce the shotcrete brittleness. We use some fiber also, and then increase the compressive and the flexible strength. So wet mix, again, wet mix yields fresh concrete typically 6 to 8 meter cube per hour versus 4 to 6 meter cube hour for dry mix. So it's much it will generate more concrete in wet methods. And so equipment is readily available because the shotcrete grind and moisturizer are not needed in the dry mix. So these are some of the application of the dry, whether you should dry or wet. Supply of ready mix concrete from the commercial batch plant is readily available for convenience. So this wet mix is readily available. Principles of nail. So we need to check that potential failure modes. So earlier one you have seen that a nail may fails different. It may fail external failure. It may fail internal failure. It may fail compound failure. So same thing like a retaining wall or MSC design walls. You need to find out the factor of safety for different things, external stability or internal stability. So here, failure mode, how it looks like. The first one is the soil nail pull-out failure. This is the pull-out failure. So this is the idea is you need to steel reinforcement. This is that transfer the tensile strength load into this soil over here because because the pull-out it just the soil nail pull-out failure. This is pull-out failure. Bearing capacity bar grout pull-out failure. So this is there is not enough bond between the grout and the nail bar. So then the bar may come out. Okay. So that is also bar grout pull-out failure. Then this is the worst case, like a nail tensile failure. So if the nail fell itself. So that is the worst. And then the nail bending or the shear failure. If this is a situation also like that, so then that is not good. So this is like a internal failure of the system, internal. So nail itself, nail bond, and then also nail failure pull out. So few things you need to check. Now this is external failure. External failure is because of the global stability, the shear failure, or the sliding failure, or the bearing failure. So same thing like a retaining wall. You studied like a external stability. You need to do that overturning failure, whole thing may retaining wall may overturn. It may slide, or it may just hold bearing capacity failure any direction. So same thing over here also external failure. So you need to check internal failure with external failure. So now the facing failure may occur, the facing wall, and then also you see the facing flexural failure is facing puncture shear failure. It may facing like a headed start failure. It may also the start where we attach this start, it may fail also. Then this is like the failure potential failure surface during construction. So what is happening? As I mentioned, this is top-down approach. Excavation 1, phase 2, like that, and then what is going to happen? The deflection you need to check. You need to see the tensile strength of the nail, and these are the critical failure surface for the different phases of construction. So phase 1, phase 2, what is happening? How much is the tensile strength? Maximum it can take. So all these things you need to calculate while designing. So basically, you need to see this load transfer mechanism. Over here, again, this is imaginary failure line. Over here, this is the imaginary failure line. This is the nail, and you see the imaginary failure line. This portion is like on this tensile on this side. This portion is friction is trying to, hold this. And then distribution of the tensile strain along the nail, it looks like this, okay? And this is the active zone over here. This is the passive resistance zone and active zone, okay? And this is the facing wall. So what is happening? The stress transfer mechanism, it looks like this. How much is the nail force? T maximum you need to calculate. You need to find out how much is the T naught, the tensile force of the nail head. Also, you need to calculate. And the facing DH is the diameter of the drill hole, and L is the length of the soil nail. So basically, again, maximum tensile force and a critical failure surface. Again, this will give you a guideline. So for any soil nail design, 3-4 things you need to check. So first thing is, what should be the length of this soil nail? What should be the diameter of the soil nail? What should be the spacing of this soil nail, particle spacing? So not only the vertical spacing, what should be the horizontal spacing of the soil nail? So 3-4 things you need to check. Okay. So these you give a guideline. So just for example, this is the height of the retaining wall is h. So this is approximately 0.3 to 0.4 times h. This is like a locus of the maximum nail force. Again, these are imaginary lines, right? So this is, again, this is the critical failure surface. Is the dotted line over here. And then how the tensile distribution of the tensile force along the nail is going to occur. So this is, and then also how much is the length of this length, okay? So beyond, so we need to find out the critical failure line, how much is that? Beyond this failure line, how much is, the active zone, basically. You need to calculate that and then find out how much is the total length. Same thing, or if you are designing a MSc wall design, how much is the active zone, how much is the passive zone, easily you can calculate the total length using that. So this is very important. How the distribution, earth pressure distribution over here. For MSc wall, it is like this. When doing MSc wall lateral pressures, you see the top surface, there is no pressure, and it's go down, pressure is increasing, right? So gamma times H times K. So K is the active earth pressure, or Ka is the active, Kp is passive, or K naught is the earth pressure at rest. So, but here in the soil nail, you see the pressure on the top is more, and then it's go down. Same thing for back wall. Back wall also. Here it is initially it is low, and then it is almost constant. Okay? So that is the difference between the lateral load distribution and this is very important to design for where is designing MSc wall design or soil nail or tieback wall. Soil nail, what are the design consideration we need to use? There are several methods of soil nail designs. Methods are used. I just added all these different methods. There is the German method, this bilinear slip surface they used. Parabolic method, so is it Davis method, French method, circular, or any shape? So again, depending on how the failure plane is going to be, like a slope stability analysis, sometimes you use the circular failure. That can be planar, it can be anything complex. So depending on that. And the kinematic method, they use the log spiral methods. Caltrans, California Department of Transportation, they use the bilinear method. Golder Associates company, they use circular failure method. So these are the different assumptions they made, and they come up with the different design methods. And there are different softwares also available to design soil nail. There is a software called Snail. So you design the soil nail using Snail. There are several types, several softwares are available also. So typical design parameters. So if you want to design, again, whatever the method you use, you need to first you have to assume something, and then use that. Then you check, okay, whether the tensile strength is okay, whether its bond length is okay, whether the length is okay, whether the diameter is okay. So all these things you need to check, and finally you need to decide. Okay. So these are the typical design parameters. So each nail has an influence area is less than 4 meters squared. Again, minimum soil spacing should be at least 1 meter. Minimum length of nail should be 0.8 times the height of the wall. Drill hole diameter of the grouted nail, it should be 100 to 200 millimeter. And then also that the minimum nail inclination should be 15 degree, 15 degree nail inclination. Ground anchor is different. Ground anchor, it can be horizontal, it can be vertical, it can be inclined. But here, most of the time, the soil nail is inclined. Okay. External stability and external stability, we just mentioned. External stability itself, the nail, inside the nail felt, and the bond between the grout and nail, all this stuff we already explained. So we need to check the external stability and external stability, internal stability, and find out how much will be the factor of safety for the temporary structure and for the permanent structures. So obviously the permanent structure, the factor of safety is more compared to the temporary structures. In some cases, it may be less, but internal stability, you see the nail pull-out, nail tensile failures. This is the most important. You can find out from here how much will be the factor of safety. This is the recommended minimum factor of safety is required if you are designing this. So then distribution of the tensile strain, tensile force, how it looks like. So here, nail tensile capacity, facing capacity, pull-out capacity. So we need to check which one is important and which one should be more for the safe design. So, you need to check the facing capacity. Sometimes it should be the pull-out capacity. It should be more than nail tensile capacity. It should be more than pull-out capacity. So all these things you need to check. So which one is more that controls, basically, whether it is pull-out controls or tensile failure controls or facing failure controls. So we need to check that using this basically tensile force distribution. Then also the maximum tensile force is you can find out using this equation, the normalized nail load, Tmax divided by Ka times gamma times H. How much is the height of that retaining wall times horizontal spacing times vertical spacing. And you see, with depth, so after certain depth, so it was uniform, and then after certain depth, this is going down. Okay, normalized nail load can be go down. Then the front pull-out capacity, you can find out using this equation. If you know the connection strength between the nail and the facing wall, so you can find out the pull-out capacity. Rear pull-out capacity also you can find out if it is connected to the bond length. And then just like this one, pull-out capacity is basically the one we already discussed, that for the ground anchor. See how the nail is anchored into the soil. Okay, so you need to know how much is that ultimate bond strength, how much is the diameter of the hole, how much is the nail length in the passive zone. So the first one is the active zone, failure line. Below the initial portion is the active, and then beyond this failure line is the passive. So we can calculate using this equation the front pull-out capacity, the rear pull-out capacity. This is again for the internal stability. And then the bond length you can find out from this table. Okay, ultimate bond length for the rock, for the cohesionless soil, that is granular type of soil, sandy type soil. For fine-grained soil, basically silt and clay. So you can find out again what construction method you are using, rotary drilling method or driven casing method, auger method. So different type of drilling method, different type of soil and rock, what should be the bond length? So that is given. Easily you can use this and calculate your in your design for ultimate bond strength. And design chart for soil nail force and nails. There are different design charts are available. So you can use that chart to design your soil nail. Again, for any design, you need to find out how much is the length of this nail, diameter of the nail, and that is the two main things: diameter of the length and nail, and length of the nail. Okay. So homogeneous ground conditions. So there are different conditions people did, like a 15-degree angle. Global factor of safety is 1.5 times minimum nail length. Factor of safety, again, for the global factor of safety, 1 for maximum size design nail force. Nail diameter should be 100, and normalized cohesion should be 0.04. So you can find out from here normalized cohesion. And you can find out the normalized pull-out resistance also. Pull-out resistance. This is normalized cohesion. And this is normalized pull-out resistance. You can use this equation. You know the ultimate bond strength. If you know the spacing, you know the vertical spacing, you know the factor of safety per pull-out, then you can find out the ultimate bond strength. And then if you know this, then you can find out how much is the maximum design nail force. So if you know the design nail force, then you can find out the normalized maximum design nail force determined from the design chart. So you can find out from there. So this is the design chart that are available. You see there are 4 cases. One is height of the retaining wall is straight, and there is backfill slope is also, there is no slope. So this is the design chart you can use. You can find out the normalized nail force. You can find out the normalized bond strength depending on the angle of internal friction of the material. Then you can use, like you see the wall is vertical, but the backfill is 10-degree back slope. So you can use this chart again, normalized design chart force, normalized nail force, and normalized bond stress. You can use this chart. Then the third one is wall itself battered 10-degree, and the backfill is back slope is the 0-degree angle with the horizontal. Then you can use this chart to find out the bond strength and normalized design force. And then the last one is like a 10-degree angle, and then also back slope is 10-degree angle. So you can find out that. So if you know this normalized design load force, Tmax, if you know this normalized bond strength, so what you can do, you need to do the correction factor for the soil nail force. So H by L by H corrected is equal to C1L, C2L. So this is the length correction factor for the drill hole diameter. C2L is the length correction for cohesion, length correction factor for global factor of safety, and CF1, the last one, the Tmax, corrected value is using this equation. Is this one you get from the chart. You do the correction, and the correction factor you can get from the drill hole diameter and also for soil cohesion. So there is a chart also here to find out C1F and C2F over here, C1F and C1L, and correction factor of C1L and C1F. So all these different factors over here, so you can calculate. So basically you can calculate H by L corrected, T by X corrected. So if you know from this chart, and you can finally, and then there is an equation for also C2L, C2F, and C3L. So over here, C2L and C3L and C3F. So this is the one you can use this equation, and this is the normalized equation. And finally, from here, you can find out the required cross-sectional area of the nail bar. So you see here Tmax S and factor of safety for the nail tensile strength or rupture, and the yield stress of the nail. You can find out that the nail bar area. If you know the area of the nail bar, you can find out the diameter of the nail bar easily. So this is the threaded bar properties, the nominal bar designation, and the cross-sectional area, and then ASTM grade, yield strength, all these things are given. So you have an idea. And finally, you can find out for maximum facing tensile force. You can find out over here from how much is the maximum design tensile nail force and how much is the S maximum. So S maximum is the maximum nailing space. So you need to check the vertical spacing and horizontal spacing, which one is the maximum. You need to take that one. Okay. Sometimes in design, sometimes you use horizontal spacing and vertical spacing are equal. But here in this case, you need to take that S maximum. So to find out how much is the maximum tensile force. Then again, internal sliding analysis you can do. So basically, I need to calculate how much is the factor of safety. Just for example, over here, the height of the retaining wall is a sloped backfill, and the nail is there. So this is imaginary planar failure surface, and the phi is given. And then what are the forces is acting? And then what are the force, the vertical load, or the normal load, shear force, everything you can calculate. Again, you can calculate the factor of safety using this equation. Factor of safety is how much is the resisting force, how much is the driving force. So that's one you can calculate, and you'll get that. So basically, ultimately, you can find out even the external analysis, you can find out the internal analysis. Again, same thing, same way you can find out the retaining wall design. So you can do that exactly same way. So how much is that for, this is for the weight of that. And then also how much is the lateral pressure will be acting, why will be acting, that will be, if you take a moment at the toe over here, and then find out the factor of safety. So factor of safety, again, same thing, it can be factor of safety against sliding. So you can use this equation for factor of safety against sliding. And then you can calculate also for the deformation of the soil nail. So that also in the soil wall, you see that initially it was like this. Now it is how much is the deformation. So you can calculate of the soil nail deformation walls. And also there is a limit for that. How much is the deformation? There is equation for that. You can calculate from there deformation of the soil nail, how much is applicable in that deformation. So, and then how much is the C value should be for the different type of soil. So this is the equation is given, so we can easily calculate how much is the deformation. So this is what I'm talking about, the deformation of the soil nail wall. Okay. And then finally, typical drainage and retaining wall. So you have to have the drainage over here. And then this is the retaining soil nail. And there is a drainage. Obviously, there is a weak fall should be there. So that same thing, same concept is basically it should not, the water should not keep more pressure on this wall. Okay. So basically, as I mentioned, for the soil nail design, there are several design chart. There are factor of safety you need to calculate. These are the different charts you need to use. Correction you need to use for that, and then for different, if it is like a 10-degree batter, 10-degree back slope, so easily you can use this chart to calculate the normalized bond strength, normalized maximum design force you can calculate, and then do the corrections. You do the corrections, and then so basically it is a corrected length over here. L by H corrected is equal to, if you get all this value from here, you will get some value. So from there, if you know the height of the wall, then you can find out L. So if you can calculate the length of the wall easily. So same thing also here for the T max, how much is the tensile strength and stuff corrected, easily you can find out. And then later on, you can find out the diameter of this from here. If you know the tensile strength maximum, you can find out the diameter of this, of the soil nail. All right. And then there are a lot of design charts that are available. You can use that. So basically L by H ratio, if I know the tensile strength of the steel, easily there is a standard, the German method, as I mentioned. So there is a given values that there are different ratios. So easily you can find out what is your soil type, and you can easily find out what should be the length of this, what should be the diameter of this soil nail. So very easy. Or otherwise you can use the software, Snail or any other softwares. All right. I just went so quickly. Can I stop here now for a minute?
Yeah, thank you, sir.
Yeah, I mean, this is just
Continuously talking from 2 to more than 2 hours.
Yeah, I mean, there's so many things you need to cover, but that's the syllabus, because we are not going to go in detail. So I'm just giving basically the overview of stuff, If you want to do design anything, so you need to, solve some problem using, all this equation stuff. Then only you know. But I'm just explaining the whole process, So now I have to complete another 2 topics. One is organic soil or peat soil stabilizations, and then also MSC wall design. So how much time I have? Like, can you want break or just I continue?
As per your comfort, sir.
So that I'll finish quickly, maybe in 1 hour.
Okay.
So let's start now. Otherwise, it's 9 o'clock there, correct?
Okay, sir.
Yeah. So let's start then. Or if you want break like 2-3 minutes, I can.
Sir, no problem.
Okay. Yeah, I'm not taking any break. If someone wants to take, just I'm just going to
Okay,
share this
you can
now.
continue then.
Okay.
Recording stopped.
Compactor and vibrator. And then also for the shallow depth, then we talked about dynamic compaction or blast, control blasting for the deeper depth. And then compaction, composer, all these different compaction. Then we talked about the hydraulic modification, get rid of the water, and then the surcharge load, preloading, and then also when you accelerate the consolidation. Yesterday we talked about sand drain. We talked about prefabricated encrest sand drain, and then PVD drain. We talked about that, and then the chemical modification. And yesterday's we talked about different chemical admixture you need to use. the conventional admixture, cement and lime, and industrial waste, fly ash, GGBS, and other. And then you talk non-conventional, you can use polymer, you can use different geopolymer we mentioned, and then durability of that. And then the last part is this inclusion, something you include into the soil. And this is basically the soil nail is also inclusion, right? So soil nail is also, this is the last portion of this. Basically, you need to reinforcing the soil, either MSE. And so we'll talk a little bit of, first thing is we'll talk about highly organic soil, how to stabilize the organic soil, and then we'll talk about the retaining wall design. So for any ground improvement technique, stability of the technique, we need to check whether the soil and technique is fundamentally compatible. Technical compliance, does the technique provide strength and stiffness requirements? So also we need to check that. Is the material is readily available? So also we need to check that. And the cost is within the budget, or what is the cost of time? So how much time is it delayed or accelerated one? So that's also need to check. And also you see that environmental considerations. So this is very general choice of ground improvement technique. So now I'm going to talk about highly organic soil stabilization. Okay. So can you see the slide now? Highly organic soil. Can you see the slide? Highly
Yes,
organic
sir.
soil. Okay, good. So
Yes,
highly
sir.
organic
Yes, sir.
soil. Okay. So highly organic soil is when the soil, most of the time, when the soil in a soil, the organic content is more than 20%, we call it organic soil. Okay. For any infrastructure design, construction, if it is more than 20% organic, we generally avoid it. Either you remove it or replace it with good soil, or we cannot just use that. So our problem is our very highly organic soil or peat, and if the organic content is more than 75%, it's called the peat as per ASTM D2067. So that is much more challenging how to construct that type of soil, because the soil is very soft, is wet, and very low CR strength. So highly organic soil or compressible soil, you can found anywhere in earth except the barren and Arctic region, and mostly it is covered like a 5 to 8%. In India, there are different places, the greater Pamba basin of Kerala, Assam, Manipur, northeastern state, some part in Kashmir or Western Ghat or Sundarban Delta in West Bengal. US, mostly the Michigan area, Minnesota, Florida Everglades, and some part in California also, they have these highly organic soil or peat. In tropical peat, generally in Malaysia, there is 3.3 million hectares of 8% of the land area is also peat. So here, so the soft soil or peat, this is a picture from Malaysia. So mostly they do, it's just that's like a water slurry. How to construct in this type of soil, it is very, very difficult. So most of the time, what they do, say use a bamboo mat, and then just like add as a temporary reinforcement, and they put sand and gravel on the top of that. So, but soil is so soft, so sometimes you just add material and just sinking. It's so difficult. And I know there is a town in Malaysia, is in West Malaysia, East Malaysia, in Sarawak, in Borneo Island. There is one town is basically they constructed everything on the construction on pile, everything is good. Remaining structures, everything is settled. And that town is really abandoned now because too much of settlement, all the that utility pipes and everything is settled, and people cannot use it. So the ground improvement method. So I'm going to talk about like a peat soil stabilizations. One of my graduate students used while I was in Malaysia. So here, this is if the depth of the peat soil is very 1 feet or 2 feet, 1 feet, you remove it and fill it with good sand. The replacement method, right? So remove and replacement methods. But sometimes the peat soil depth is quite thick, so it is not economical to remove whole soil. So obviously, if you want to construct on this type of soil, you see the sinking excavator. So even excavator cannot, it can take the load of the excavator. So the problem is, if you want to put any structures, good structures, you need to use pile foundation. So, but sometimes it's obviously pile foundation is expensive. So people are, if the soft soil is very high depth, so you can stabilize some portion of the soil if the water content is less, and then you can use this chemical soil stabilization technique. The problem is sometimes the water table is too high. Sometimes you need to pump the water out and then reduce the water content, and then you mix it. Or sometimes you take out the soil sample and then mix it and then dump it there. There are different techniques I have seen there in Malaysia. So the pile embankment is expensive, but lightweight field, sometimes the soil strength is so low, so we need to use some lightweight field over there. Okay, and also the thermal precompressions also can be used. So I'm going to talk about here chemical soil stabilization techniques. So this is how the sample looks like. So when you collect soil sample, it's very soft, and the water content is very high. Okay, and then soil has a lot of fibers. So mostly is decomposed organic matter. So mostly if you want to do experiment on that type of soil, you cannot just keep it in the oven. First, you have to put it in a tray for sun dry, and then keep it in the oven. Also, sometimes for this peat type of soil, because organic content is too high and the fiber is there, instead of 100-degree, for the moisture content is 105 degrees Celsius for 24 hours, you need to reduce the temperature like 65 degrees, otherwise it will burn. So 65 degrees for 24 hours, and then you grind it and pass through 3.3 millimeter sieve. So it depends how much fiber you need, and then you do for different tests. So we collected the soil sample, and then we grind it, and then oven dried, sun dried first, and then oven dried for 60 degree, 65 degree, and then test different tests. So basically, physical test and geotechnical properties test has been conducted. Natural moisture content, degree of, so here it is little bit different from the normal soil. One is the degree of decomposition of the test and the fiber content test. Generally, we don't do this for normal soil. And also we do loss on ignition and organic content test, and also do the pH test. So these are the different tests generally you need to do for organic soil or peat soil. Geotechnical properties in the standard Proctor and UCS is common, and then also compressibility test, that is the consolidation test, because it has a fiber. So if you use normal odiometer test or consolidation test, it will not give you the correct results. So you need to use the bigger diameter cell called the row cell, and there is a cell, bigger diameter cell, and then you need to use a large quantity of sample, and then there is a rubber balloon. You can pressurize using rubber balloon, and then consolidation takes place. But advantages of that also, you can measure the pore water pressure from this consolidation test, the row cell consolidation test. So these are the different tests, different sample we tested. So we designated M1, M2, M3 to M8. And you see the first, second row, you see the natural moisture content. You see the moisture content is 587, 600, 400. So this is not a soil, correct? This is like a slurry. So how to construct on that type of soil is a big challenge. So and then degree of decomposition. So it is H1. So there is a scale from H1 to H10. So more number is more decomposed. More number is more decomposed. So here in this soil, M1 to M8, so M8 is the more decomposed, So what is going to happen if it's more decomposed, and finally is after decomposed, it will be converting from organic soil to mineral soil, correct? The loss on ignition is initially was this 96 for this one, M1, and 44 for this more decomposed. The loss on ignition is also decreasing. Organic content here, M1 is the highest numbers, 95. So this is definitely peat soil because the organic content is more than 75%. So M8 is over here. This is 42%, 42.53%. Specific gravity you see over here. Organic content is fiber is is more fiber, the specific gravity is lighter, but you see it's more decomposed. You know, it is converting from organic soil to mineral soil. The specific gravity is increased. Fiber content is also decreased for more decomposed. Initially, for peat, it was 65%, almost 66%. For M8, it is 31%. Liquid limit, you see here, the liquid limit is, you see 150%, 150%. And then for M8 is 69. And then pH, one thing you noticed here, the pH is less than 7. So it is acidic. Okay, the pH is less than 7 is acidic. So if you want to stabilize using chemicals, so then we need alkali, right? So for the lime or cement, we need alkali. So if it is acidic, then it is not going to work, right? So what you need to do, you need to add more cement or more lime, or you need to do some treatment, make it like a as per given by the Edel, and the N is the loss on ignition. So you can find out how much is organic content. So this is, I'm not going to go in detail. So this is the degree of humidification. It's a very crude test to find out how much is the degree of decomposition. Most of the time you take a peat soil from the side and just squeeze it. So what type of water is coming out from here between your fingers? So you can find out what type of the degree of decomposition. Okay. So there are 10 H1 to H10, and this is called the von Post scale, von Post scale. So you can find out what are the different category. So the H10 is completely decomposed peat, so no plant fractions, and when it's squeezed out, so it escapes the peat, wet scrapes between the fingers. So again, wet peat is coming out. So sometimes depending on the fiber, content, or depending on the degree of decomposition. So depending on what type of water is coming out, only water is coming out, or peat is coming out, so all these things you can find out from there. So now, as I mentioned, we did compaction test for M1 and M8, all these different type of soil, and then we noticed that the more decomposed material and the specific gravity was higher, and then obviously the standard Proctor, the specific gravity is higher, means it will give you more density. So M8 was, you see over here, M8 was more decomposed. Specific gravity was 1.82. That's why it gave the maximum strength. So M8 is star over here. That is the maximum strength it can give, maximum dry density, but the optimum moisture content is also less. Okay. Then, so this is a sample collection we did. This is two of my graduate students that time. So we used, we fabricated this. This one you see here. This is the soil sampler. Okay, we fabricated that, and to collect the soil sample. And on the left corner over here, this is the row cell for the consolidation test. Okay, so and you have to really transport very slowly, and then bring it and place it into the row cell to do the test. So this is the sampler we fabricated. So basically, just like a syringe, injection syringe. So basically, there's a plate over here. If you push it into the soil, and then you just drag it up so that it would create a vacuum and then hold the sample, because it's so soft, it is difficult. Then these are the different properties of the row cell consolidation test. You see over here, so again, the type of peat, as I mentioned, is a fibric peat over 66%. If it is over 66% fiber, then it's called the fibric peat. If it is 33 to 66% fiber, then it's called the hemic peat. If it is less than 33%, it's called the sulfic peat. There are different type of peat. And then von Post scale, it is H4 or less in this case, and H4 or H5. If it is sulfic, then it is H7. So, and then we did all the different tests, and then finally we did the consolidation test over here. You see here, void ratio is 10. So most of the time the void ratio is 1 and less, right? If it is a pure clay, it is a little bit more than 1, right? So the void ratio is 10. So it's very, very compressible. And this is using odometer test. This one, the same test using odometer, and same test, same sample using the row cell consolidation cell. So you see the compression index values. Compression index values is the row cell is 3.48. And then odometer value 4 point something. It's a compression index. It will give you, so settlement you can calculate from the CC value, correct? Settlement is basically CC times H divided by 1 plus E naught log of 10 plus sigma naught plus delta sigma divided by sigma naught. You can find out from there. So basically CC is important, right? So CC is the compression index. Compression index more, it will give more settlement. So it is very high. Most of the cases compression index is less than some fraction. So now it is 3, 4. This is really extremely high. So compressibility index, that's why we just normalize that compressive index values. And then also peat soil, it is very important to calculate not only that primary consolidation, we need to calculate for the secondary and tertiary consolidation. Okay? And this is the relation between this compression index, primary consolidation, and the secondary consolidation over here. And you see the secondary consolidation is almost 1/5 of this, or 1/10 of this, the compression index. Okay. So, and then, so basically what we did in this is the properties of the peat soil. And then we did all the basic tests, and then we stabilized that to increase the strength gain. So here we used different types of chemicals. So most of the cases, the chemicals is the fly ash, lime, all these different chemicals, and we used different sodium sulfonate, sulfate, and calcium chloride also. So here, this is the curing period. So you see the cured, when you prepare the soil sample, it cured under water. Just to simulate the situation, the peat soil has very high water content over there. So this, all the mold is half submerged. And then, because the soil is so soft, even the excavation, if you push it, the soil will come out. It will be brittle. So that's why we developed we put it in a split into two, and they just push it using the spatula, and then divide it into and collect the soil sample. So, and then we measure the soil sample, and then we test it for UCS test. Basically, it's 50 millimeter times 100. So for that particular peat soil, we used ordinary Portland cement, 5 to 25%, because the organic soil you need to be more compared to the mineral soil. And then we use quicklime, 2 to 8%. We use fly ash, 5 to 25%. And we use combination of fly ash and quicklime. So you use 5, 10, 15, 20% fly ash, and then we just varied this 2 to 8% quicklime, for different combinations. So this is one. And then we just check how much is the original strength of the UCS strength. So we have that. And then how much is the with time, that 7 days, 14 days, and 28 days, how the strength is increasing. Obviously, you can see here, this is the left side is the lime, and this is for the different type of cement. So obviously, the more cement, 25% cement, the strength is high. But this is the lime, strength is almost close to 10% cement. Then this is the graph with combination of this is the original fly ash. This is the combination of fly ash plus lime. This is also the combination of fly ash plus lime. What is happening for different combinations, and we have seen that with the fly ash content is increasing, the strength is increasing also. So not much, but a little bit increase. And then this is the scanning electron microscope of original peat soil. This is original fly ash, looks like. And then when you have the 20% fly ash and 20% fly ash plus lime, so you see is more dense structures, and the strength. That's why the strength is increasing. UCS strength is increasing. So over here, in 20% cement, you see is the strong bond form because of that. This is 5,000 times magnified, and this is 5 micron. So that's the reason the strength is increasing for the cement. And these are the conclusion for that test. So basically, over here, the result is the peat sample increases 5 to 10%. But so when you use, so I'm just going to go here, that when you use 5% OPC plus fly ash and 2% calcium sulfate stabilized soil better than the chemicals we used. And then also when you use like a 20% OPC and when you use 6% lime and 20% fly ash, that will give almost 70% strength when you use 20% of cement. Okay, so the first here, this is the untreated one. So these studies I have not presented here. This is one of our other studies. What we did, like because of the fly ash, that the peat is basically is acidic because of it has humic acid and fulvic acid. We neutralize that acid with sodium hydroxide first, and then you add it with different chemicals and different stabilizers. Also, that paper. So basically over here, you can find out all these, whatever I just now presented in this journal paper. And I have some more, but I have not included over here in this. Okay. So this is basically now the organic soil stabilizations. Then I'm going to talk about now the earth structures or earth retaining structures. Okay. So again, this is totally the last topic. Basically, we're talking about earth retaining structures or MSC wall design. External stabilized system, that's in situ wall, the gravity wall. Internal stabilized system, that's the reinforcing coming into pictures, the reinforced earth, or it can be used geotextiles material. We'll talk a little bit of geosynthetic material, and then in situ reinforcement. You can use soil nailing. You can use reticulated micropiles. So micropile is basically another one type of soil nail, smaller diameter piles. So obviously now this is the last method, as I mentioned, the soil stabilization is something you need to include into the soil because soil cannot take tension. So what you need to do, either you include some reinforcement or you can use some geotextiles or geogrid, okay? So that it can take the tensile load, soil can take compression load. So that's the MSC wall. So, so therefore the inclusion of tensile force member in a soil can significantly increase the strength and load bearing capacity, okay? So soil can take only the compression load. So again, the resulting in the reinforcing soil is called the mechanically stabilized earth. Mechanically stabilized earth. So obviously we can design mechanically stabilized earth retaining wall, right? So often MSC is used in slopes when the slope is steeper. So if you use a mechanically stabilized earth, you can make a really exact vertical wall, so that you, instead of if you make a slope, so you can lose some space. So here you can utilize whole area. This method of intermediate alternative between the earth slopes and the retaining walls. Retaining wall or reinforced. So I'm going to talk about a little bit more about the reinforcement. So here, and then also we talk about what are the different reinforcing material used to stabilize the soil. So modern form of reinforced earth was introduced by the Henry Vidal in 1960. Reinforced earth is internally stabilized, flexible structures to assist dynamic and structural load and the foundation movement and settlement. So advantage of MSC retaining wall or any structures is it can resist more dynamic or earthquake load, and the construction is much quicker compared to the conventional retaining wall. So reinforced soil or mechanically stabilized soil is a construction technique that consists soil that has been strengthened by tensile strength. So the soil can take only compression. So you need to put some metal strip, you need to put some geotextiles or geogrid. Okay. So reinforced earth is a type of retaining wall. The mechanically reinforced earth is also called the gravity wall. So these are the few things. And again, reinforced earth is a combination of soil, which is strong in shear and compression, and reinforcement, which is strong in tensile strength. So that's the reason you can use, so basically the solid structures. Okay. So beneficial effect of soil reinforcement. So increase the tensile strength of the soil mass. That is one. And then the shear resistance developed from the friction between the soil reinforcement interface. So we need to find out how much is the friction between this reinforcing element, that is steel, or maybe the geogrid or the geotextiles and the soil. And then the design, the reinforcing steel, the free draining granular soil, adverse effect of the water pressure of the soil or the cohesive soil can be avoided. So again, most of the time is we use the granular material so that all the water is gone out, so that it will not give any, if the water is there, water also give you a pressure to the retaining wall, in conventional retaining wall. So we want that, we don't want that. So water will give pressure, means it will give you additional pressure, whatever the soil pressure plus water pressure. So advantages, as I mentioned, is the flexible structures. It can deform, withstand deformation and foundation settlement. It and equally suitable for good foundation. Due to their flexible structures, it can withstand, as I mentioned earlier, earthquake stress better than the conventional rigid structures. Reinforced earth structure can be constructed speedily and also in stages. It can do in construction stages, or you can do the construction very quickly. Reinforcement, particularly in geotextiles fabric, as a lightweight and available for convenient sizes. It is a factory product, so you can lay the it comes in a roll, so you can do the construction very quick. And reinforced earth is structures economical, giving 30 to 50% cost when compared to the conventional concrete and retaining walls. It's less expensive. So you can use either a different type, or you can use either metal strip, mild steel bar or strips. You can use high tensile steel bar or strips, flat strip or mats. You can use geosynthetic materials. It can be geotextiles. It can be non-woven and woven. I'll show you some pictures. And then geomembrane. It can be geogrid. It can be geostrips. It can be geocomposite. Fiberglass possesses high strength and it is corrosion resistance. People are using in concrete fiberglass. There is no corrosion. It's lightweight and more strength. Only thing is you need to check the bond. Bamboo strips or mat deteriorates quickly, but for the temporary, you can use that for temporary structures. Okay, and also you need to do some treatment. So now, if you're using metal strip, obviously when you are designing it, you need to either use the galvanized steel, or you need to use some painting to prevent corrosions. So galvanized steel is used as reinforcement, and the corrosion we are designing, you need to use that. Obviously, the corrosion is inevitable, so you need to use like a 0.25 to 0.05 millimeter per year. Every time will be every year will be corrosion rate. Actual thickness, that's why you need to do the design thickness plus R, the rate of corrosion you need to include, and how much is the lifetime of the structure. So mostly, generally we design for 30 years or 40 years. Although we know that metal strip is going to deteriorate, people in US, at least I know, people still use metal strip instead of geotextiles or geogrid. So I'm just going to talk a little bit of geosynthetic material. Geosynthetic materials, the Balmain material, it can be used for anything. Geotechnical or geoenvironmental applications. It can be used for separation. It can be used for reinforcement. Here, in this case, we are using as a reinforcement. It can be used for filtration. It can be used for drainage. It can be used for liquid barrier, just like an impermeable barrier, as an like a geoenvironmental applications. So if you contain any contaminants or leachate, you can use that the liquid barrier. So I'm not going to go in detail over here. Drainage, filtration, separation, and reinforcement. There are different purposes. You can use that but here in this case, you will be using as a reinforcement. So, and then there are geotextiles and geogrid and geomembrane. These are the three main geosynthetic material. It comes in geosynthetic materials are geotextiles, geogrid, and geomembrane. So textiles means it's like cloth, right? So again, it can be geosynthetic material. It can be polyester, can be polystyrene, it can be polyethylene, it can be polyacrylonite, It can be polyvinyl chloride, PVC. So any type of material. So it can be high density or low density polyethylene material, synthetic material. Okay. So it can, people are using also natural fibers like a cotton and jute or bamboo as a geotextiles or material. So we need to see, although the problem is if you insert the steel, there is a problem with corrosion. If you insert that geogrid or geotextile, geogrid, again, it is it is going to corrode. Also not corrode, but it will be UV light deterioration due to the UV light, and also for, so over here there are oven geotextiles. There are different types like a oven and non-oven. There are different types of geosynthetic material. I will just go quickly. Geotextiles, it can be geogrid, it can be geonet, it can be geomembrane, geosynthetic clay liner. So there's a clay, bentonite clay, and then the top there is geosynthetic on the top. Geopipe, geofoam, geocomposite. So there are a lot of things. Geofoam generally used for peat soil. Just for example, people are using like a geofoam or foam concrete on the top of stabilized peat, because the strength is, is very, very low, that bearing capacity. Geotextiles, it looks like this is the cloths, is the, the pattern is there, oven filament. So it is basically, there is horizontal direction, vertical direction, there is a pattern. So that is oven. And if you see the scanning electron microscope, how it looks like on the right side, it's the oven filament, multi-filament. So we have, it's not only one thread, it's several thread, multi-filament, but it is oven again, just like a cloth. The last two pictures is the non-oven material. So this is not doesn't have any pattern like a cloth, but this is, and then the needle punctured and bonded with the heat. Okay, this is non-oven. So geogrid here will be using that mostly for retaining wall design. So it looks like this geogrid. So it can be uniaxial, it can be biaxial. Most of the cases it is high density polyethylene type of material. So you see here, this is geogrid. There are different company has different geogrid, mostly used for reinforcement. So this is geonet, how it looks like. This is geomembrane. So basically for the containment, so water really permeability is, water cannot pass through that in geomembrane. So generally geoenvironmental application, people use this. This is geocomposite. So it can be mixture with anything. Okay. And then these are the summary of that. So geotextiles can be used for separation, reinforcement, filtration, and drainage. Obviously, it cannot be used for containment. Geogrid is, that is the word interested in. So it can be used for reinforcement. Geonet is obviously the drainage. Geomembrane is also for containment. Geocomposite you can do for anything. So now this is the basic of geosynthetic material. So we'll be using most of the time geogrid now for MSE wall design. So this is like a mechanically stabilized art. So we have MSE reinforcement. It can be metal strip, it can be geotextiles, it can be geogrid. And then there's the drainage layer, and there's the facing wall. The facing wall is the prefabricated concrete blocks just attached to that. And that's why this construction is very quick, So how it looks like, reinforced zone over here. This is drainage layer, reinforced zone. This is the retained zone over here. So most of the time is a normal conventional wall. There is a retaining wall, and there is a backfill, right? So here, even these constitute the wall itself. So basically, it's a reinforced zone, and then the next one is the retained zone, basically. So while doing this stability of this retaining wall, so we need to see the internal stability and then external stability. Okay. So here the MSE wall is, you see approximately 57% MSE wall conducted in US utilize the metal strip. Although we know that it's going to corrode, but still in US, 57% uses steel metal strip. Service life is 75 to 100 years. However, early complication, the corrosion is reported. So it can be used for bridge abutment. It can be used in highway. It can use railway, commercial and residential area, raised elevation, bridge approach, and the hilly area. Most of the cases is very common here in US in the highway approach, and and mostly the highway approach. So we have seen this. It's very common. So while designing, doing this designing consideration of the retaining wall, so we need to check, as I mentioned, the conventional retaining wall. We do the external stability analysis to find out the factor of safety for because of the lateral load, how much is, whether it's going to overturn or whether it's going to retaining wall is going to slide, or is the bearing capacity failure. 3 different factors of safety you need to calculate for conventional retaining wall design. Here in this case, we need to do the external stability and we need to do the internal stability also. So internal stability checks involves the tensile strength and pull-out resistance, and the integrity of the facing element. So obviously you put an reinforcement inside this. If the reinforcement breaks, so then what is the point? So that is the tensile, determine the tensile strength. Then you need to find the pull-out resistance if it slips. The same thing we mentioned for the grout anchor. And also integrity of the facing wall. Also, you need to check that, okay? And then external stability is the same as overall overturning, sliding, and bearing capacity. So this is how it looks like, MSE wall. So this is sliding, whole thing is sliding, whole thing is overturning. There is bearing capacity failure and deep-seated failure. So using metal strip, how we are going to do that? So you see here the main component, the backfill with granular soil. Ideally, it should be granular soil so that the water can drain quickly. Metal strip, which is thin, widespread, placed in a regular interval. You need to know how much is the vertical spacing, how much is the horizontal spacing, all these things. And the cover of the font space, we call it scheme. So this is the figure over here, and this is the scheme. And there are different types of schemes that are available, mostly the concrete block. And then there is a tie over here, and this is the horizontal spacing SH, and this is the vertical spacing. This is how it looks like, retaining wall for the metallic strip under construction. So mostly you can see here, the metal strip is there, and then you compact it with the soil. Okay. So, and then this is another geotextile. So put a layer of geotextiles, then put a sand layer, and then compact it using vibration because it's granular soil. And then after you compact it and then fill it with soil, then put another layer and compact it, then put another layer like this. So this is geotextile reinforced retaining wall. On the facing wall, you can see how it looks like. So if it is a geogrid, or sometimes you put a gabion wall, the facing wall, so it's like a cage type of structure. So you put a stones inside that, and that can be the stack on that. And there is a gabion wall, and the geogrid is attached, and then fill material. Geotextiles or geogrids, this is uniaxial or biaxial, depending on the situation, you can use that. And then there is a concrete facing wall on the top, so that can be used. So again, depending on your design, so you can use change the length of the geotextiles. So depending on your how much the loading is coming. So this is a geogrid, and then how the facing wall looks like this, the concrete, and then fill it with sand or gravel material, and then put a layer of geogrid or geotextiles on the facing wall, and then put another layers like that. So this is again over here in Southern Illinois. I took some of the pictures how it looks like. This is a metal strip, and then also there is a concrete facing wall over here. So concrete facing wall, how it looks like. This is over here. You can see here there is a connector, just like this. There's a groove here. The metal strip can go inside, and then put a nut bolt there. So this is, you can see the horizontal spacing over here. So how it looks like. So this is you see here in that construction. Last lecture you mentioned that the PVD the same place. So this is the horizontal directions. This is and then after you fill it with sand and then increase that the facing wall, then you put another layer, and then you put another layer of reinforcement. So this is how it looks like, and this is the metal strip. How it looks like, there is a holes that can be attached. So you can see here, this is the reinforcement strip, and this is the gravel type of material they used, and this is the horizontal spacing over here from here to here, and this is the next one. So when you now after this, they will fill it with the granular soil, and then the next one will be attaching on this groove over here. So this will come horizontally. So That will be the vertical spacing, and this one you can see the horizontal spacing. This is how they do with this MSE wall. So this is the concrete block already. So you can see now this is the horizontal spacing. From here to here is the vertical spacing, and then also the concrete facing wall can be anything. So from the outside it looks like this. So there are different. I mean, this is very common these days everywhere anywhere in the world now. So this MSE wall design. So you can really construct a vertical wall. Okay. So now the thing is how to design that. So again, we use the concept of the lateral arc pressure theories, and so basically there is the total length you need to find out, and again it's a failure line, 45 degree plus 5 by 2. How much is the friction angle of the material of the soil, and then LR, it is the Rankine's length inside that failure line. And LE is the total, LE is the effective length. So most of the time, the reinforcement should be beyond that failure line. Otherwise it's not going to work. And then finally, the total length of the reinforcement, you need to calculate LE plus LR. You need to calculate the total length. And again, you need to know how much is the active arc pressure, how much is the surcharge load if there is any. You need to calculate. And you need to know if there is a load. How much is the load distribution from there? And I'm not going to go in detail. So here, and then first thing is you need to know the tie force. How much is the tie force developed on this? So depending on the active arc pressure, area of the wall to be supported by the tie. So again, you need to the retaining wall design. When the wall is moving out from the soil, that is the active pressure, and the pressure distribution is like a triangle. So from the top is 0 and is going down, and then the lateral arc pressure, the total pressure at the base of that retaining wall is gamma times how much is the height of the wall, and then arc pressure coefficient K. So if it is active, then it should be Ka. So K is, or Kp, or passive, or K naught is depending on the angle of internal friction of the material, phi. Easily you can find out K is equal to 1 minus sine phi by 1 plus sine phi. So easily you can calculate that. So first thing is the tie force you can calculate. And then you can find out the thickness of the metal strip you are using in design load, how much is the corrosion rate, you can find out from there. And then you need to calculate first two internal stability factor of safety. One is the factor of safety for the tie failure. So you can find out the factor of safety of the breaking or tie of the tie. So you can use this equation where W is the width of the tie, T is the thickness of the tie, width of the tie, thickness of the tie. If Y is the tensile strength or the yield strength of the tie material, and this is the one we just calculated, how much is the active stresses and the horizontal spacing and vertical spacing. So this is the factor of safety we can calculate against tie failure. And then this is the internal stability. And then reinforcing tie, how much is the friction between this reinforcement and the soil itself. So you can calculate by using FR, how much is the effective length, how much is that the width, how much is the vertical stress, and how much is the sigma. You see here, sigma mu is the soil and tie friction. It is not for the soil only. It is soil and tie, how much is the friction between the reinforcing material and the soil. So if you know that, so then if there is a pull out, first one is the breakage, reinforcement break. So that is not good. So if it's a pull out also, then the purpose is not solved. So then you can find out the factor of safety for breakage. So we need to find out how much is the LE, how much is the W, how much is the vertical stress, and how much is the friction between this, the friction between the sand or the granular material and the geotextiles material or geogrid material or the reinforcement material, all these things. And then you need to find out the total length, as I mentioned, the failure lines, how much is the inside the Rankine's, LR, and how much is the length for the LE. So same way you can calculate how much is the total length. You need to know that LE plus LR. So LE is given by this equation. That is the effective length. That is the one, when there's the friction is important over there. And then LR, you can calculate, using this equation, H minus Z divided by tan 45 plus 5 by 2, pi 1 by 2. So the total length will be LE plus LR. That is the last equation over here. So we can find out the total length. So what is the step-by-step design procedure? So we need to know how much is the height of the wall. We need to assume internal stability. You need to assume that the factor of safety for breaking, factor of safety for the pull-out, and then there is the internal stability, two internal stability factors for breaking and factors for pull-out, and then you do the internal stability, external stability, you do the factor of safety for overturning, factor of safety for sliding, factor of safety for bearing capacity failure. So same thing, you can do it for over here. So for most of the time, you see here, MSC wall design, it can take more load on the top. So basically, you can decrease the size of this retaining wall as you go down below the ground. So basically, and that very much more economical. So again, you need to find out. So find out the taking at the moment at point B, and then how much of the load is coming, how much is the load for this area, how much is the load for this area, and then you can easily find out how much of the lateral load is coming. Also, you can calculate. So exactly the same way you did for factor of safety for sliding, how much factor of safety for bearing capacity, all these things you can easily calculate. So idea is basically you need to calculate the braking, factor of safety of braking and pull out. That is the internal stability. And external stability, the same thing for the conventional retaining wall design, factor of safety for the sliding, overturning, and the bearing capacity. So now this is for the geotextiles material over here. So earlier was a metal strip. This is a similar thing. But only thing is we need to, again, this is the allowable tensile strength. You can find out from the ultimate tensile strength. And then also you need to find out the ultimate reduction factor for installation damage. Sometimes because of this geogrid or geotextiles material when you're installing, and that may create damage. So that's why you need to do some reduction factor due to creep, reduction factor due to chemical and biological degradation. And all these factors, there is a standard value from the Kroner 2005. So you can find out that. And then obviously, when you use the geotextile, there should be some lap length over here, and there should be some lap length. So basically, you see over here, LL. So basically, when geotextiles, put a geosynthetic material, put a granular soil, and then you just put a little bit of lap on the cover, overlap the cover. There is no skin over here. And then you put a layer of sand layer again, and then put a geotextiles, and then put the lap length over here. So basically, what you need to do, you need to find out LE and LR, same, the Rankin's failure lines, and then 45 plus 5/2 angle. And then, so this is geotextiles. The only thing is here, you can do same way exactly how much is the T allowable. And then the vertical spacing, you can find out how much is the factor of safety for breaking, 1.3 to 1.5. And the friction angle sometimes between these geotextiles and the angle of internal friction. So most of the time, if it is not given, you can use like a 2/3 of angle of friction of the granular soil. So you can use that. And then again, LR is equal to, you can use this equation, LE is equal to use this equation, and then total length of the geotextiles, LE plus LR, you can easily find out. So only thing is here, how much is the lap length? That one, you can use this equation over here. Is SV, you need to know how much is the vertical spacing, how much is the factor of safety for pullout, and then angle of internal friction for the geotextiles and the soil backfill material. And it should be minimum 1 meter. It should be minimum 1 meter or 3 feet. Okay. And then if you know that, and then again, the same way you can calculate the external stability one. Okay. So again, the external stability is basically the factor of safety against sliding, factor of safety against overturning, and factor of safety against bearing capacity failure. So, so that's all mostly, for this MSC wall design. All right. Any questions? Anything? So I have not solved any problems. This is just, the theory is very easy things, imaginary failure line and conventional retaining wall design, how much is the active pressure? So we need to, again, in the conventional design presses, how much is the lateral arc pressure? So you need to know how to calculate that, and easily you can find out. Okay.
Sir, there is one query in the chat box. In which field cotton geomass are used?
Which one?
In which field cotton geomass are used?
Okay, cotton one is not very common. I know that people are using for the temporary, I know that people are using for like a bamboo mat or jute geotextiles sometimes. And it's very rare, people don't use much, So, yeah, I mean, although in the slide I mentioned, but I think it's not very common, and depending on again availability of the material. People are using also different types of fiber, right? So into the soil, so high density polyethylene fiber, people are using sisal fiber. There are a lot of fibers. Also, the coconut coir fiber, also people are using as a reinforcement, is a disintegrated fiber. So a similar type, the cotton geomass or, but it's not easy to make, but, I have seen some paper people, mention that. But the cotton fiber, I think people are using in India, I know. And then also the bamboo mat, also I have seen in Malaysia, people use that bamboo mat fiber or bamboo mat also for peat soil separation and other. So again, depending on the situation, you can use. So most of the cases, as I mentioned in US, mostly people feel 57% uses the metal strip. It's easy. And then geotextiles and geogrid also people are using that. And then I know that GeoJute people are using long back, maybe 30 years ago. One of my friends, he uses in West Bengal, I know the GeoJute reinforcement in certain area. Any other question? Anyway, I have to, I just gone just very quick, to cover all this topic, but
Sir, someone was asking for the slides. If you can share, sir.
yeah, I think I can send, if you can create like OneDrive or something, I can share all my slides, whatever I have, and then you guys can share to the participants.
Yes, sir. Yes, sir. You can please share to Chore, sir. I'll share in the to all the participants.
Yeah. Please do that. And then it seems like I need to prepare some quiz
Yes,
for
sir.
Saturday, correct?
Yes, sir. Yes, sir.
So, so that will be, I think, yeah, these slides will be required, but I'll be just only objective type and fill in the blanks type question, correct?
Yes, sir.
Yeah. So only A, B, C, D type or fill in the blanks and, covering everything. So there'll be several questions then. I don't know how many, maybe.
So I think 20 to 30 questions will be enough, sir.
20 to 30 questions from all topic? Yes.
Maybe, sir.
I think maybe 50, at least 50 to 100 maybe.
Okay, sir.
For every topic, at least 10 questions. Maybe.
Yes, sir.
Okay. I mean, very easy, but
We'll discuss that on tomorrow,
yeah.
sir.
Okay.
No question, sir. Actually, no question, sir.
Okay.
Everything is, yes, self-explanatory. You are explaining well.
Okay, good.
Thank you, sir. Thank you, sir. Thank you.
Already, so next, tomorrow is the only one class lecture, I think, is on sustainability of engineering and then sustainability improvement.
Yes, sir.
And that's all. Okay. And then we will talk about more about the participants. I don't know who is the participants even. All right. Thank you so much.
Okay. Thank you, sir. Thank you
Thank
so
you, sir.
much.
Thank you.
All right. Thank you. Good night.